Okay, good morning, everyone. So Dan, unfortunately, has got a cold, not COVID, but is not here today, unfortunately. But we've got a really exciting day of more talks, and we've also got the virtual poster session today. So our first talk is by Nikki Wright, who is joining us online from Australia. So Nikki, if you're there, we'll switch over to you.
I'll go and get started. Thank you so much for inviting me to talk. And sorry that I'm not in there in person. I've been trying to pay along as much as I can, given the awful time difference for me. And so today I'll be talking about long-term changes in sea level based on reconstructions of paleobathymetry and ocean basin volume since the Mesozoic. So I also want to thank Ken for shouting out to my paper yesterday as well. That was pretty awesome. And so I'll give you a bit of the detail of what's in that paper and how we reconstruct paleobathymetry and sea level from it all. So just to start off, there's lots of different sea level reconstructions, and they're all created using a variety of methods. I'm not going to take you through every one that exists in the world, but I'll just show a few to give you examples. So here we've just got a few, and I'm just calling them based on plate tectonic models. So generally based on ridge volume. Here are some of the older ones. One of the ones I'll be referencing a lot today is Muller et al. 2008. So this is Dietmar Muller's one from 2008 that used paleobathymetry to reconstruct it. So it was underlined by a plate tectonic model and age grids, and goes back to 140 million years ago. We've also got Christian Berard's work based on a completely different plate tectonic model and based on geodynamic reconstructions. And then in Muller et al. 2018 and Carlson et al. 2019, both used the same plate model, which is Muller et al. 2016, but they incorporate different components. In Dietmar's 2018 work, he incorporates dynamic topography, as does Carlson et al., but they also incorporate water cycling. And so you're getting very different results based on similar plate models. And everything here, I don't know if you can see the fate lines very well if you're in person, but there's just huge magnitude. More traditionally, we've got these, what I'm calling just stratigraphic methods, all giving you different orders of magnitude of change. And then we've also got Venemer's work based on the strontium isotopes, it's pretty cool. And so just overall, you can see we know that sea level is probably higher in the Cretaceous compared to present day and lower earlier in the Mesozoic, but there's a huge range of hundreds of meters between some of these sea level curves, and the timing of everything changes so much. And so we asked ourselves, using a more recent plate tectonic model, how does sea level vary? Just can we add another one to the mix? But can we also better quantify the contribution of some of these components? Take a look more at that paleobathymetry. So I guess just very briefly on how the solid Earth influences sea level. So on timescales longer than 1 million years, a lot of the variations we see are caused by the solid Earth processes. It's the changes in container size that is influencing the sea level all the time. And so that results from faster seafloor spreading, and also just different, we've got changes in sedimentation, or we've got more volcanism, changes in your continental area, dynamic topography, water fluxes also influence sea level as well. And so I'll be talking about these four primarily. I won't be talking about dynamic topography. I'm just going to put a big cross through it. I know it's really important. And there's some great papers that have come out in the last couple of years that look at the influence. But yeah, my work is more focusing on some of these other components of paleobathymetry. And so to calculate sea level, what we do is we convert everything into paleobathymetry. And so here I've got a set of age grids. So this is age of the oceanic floor that we reconstruct here at Sydney Uni. A lot of the information is based on magnetic anomaly data from the ocean floor. And so we have pretty good constraints on those ages. Gets worse back in time. But we use this and we can convert it all into depth space. So you get these, you get some pretty simple reconstructions further back in time and ignore some of my artifacts in the bathymetry. But you can also see you've got volcanism on the seafloor. And here I've also reconstructed some of those passive margins. so we can incorporate that into our sea level reconstructions. And so how exactly does this work? So to reconstruct paleolithometry, this is what they did in 2008, and is pretty similar to what we do now and what other people do, is we first calculate depth to basement. So we have our age grids from whatever plate model that you like, and we convert this using some kind of oceanic subsidence relationship. And there's a lot of different ones you can use. So here in the 2008 paper, they use Stein and Stein, which is also referred to as GDH1. Once you've got your basement depth, we then add some kind of sediments. And so in 2008, they used a latitude and age dependent model of sediments. So it was a global relationship they came up with, and it was quite simplified. I guess doesn't take into account like any kind of mechanism as to why you would have sediments that much higher in the higher latitudes. But yes. Then we add some kind of, they add the large igneous provinces, so some kind of model for what lips may have looked like for the ones that they have good data on. And then you combine them all together and you get, reconstructed bathymetry and something that kind of looks like this. And so, I'll take you through some of these different components. And so I guess the first question is then, what is the influence of the plate tectonic model itself on sea level? So I have already shown you this curve on a different plot. I've shown you something similar to this on a different plot. So you've got this 2008 model, and so we can calculate the mean age of the seafloor from that. We can calculate mean depth. I actually calculate mean volume as well, but I haven't shown it here. And from this, we can calculate then changes in sea level over the last 140 million years. In 2016, the plate model was extended back to 230 million years ago. And then we also calculated, or I've also calculated like an age misfit through time. So this is based on like the misfit of the age of the seafloor age grids versus the magnetic anomaly data that goes into it. So we have pretty good constraints. It's pretty low error during the last 80 million years, and then the error increases as you go back in time. This is not like a really true uncertainty, I will say, because there's like unlimited configurations you could probably have for some of these different plate boundaries in the Pacific and in the other parts of the ocean. And we can propagate that error to look at the depths in the sea level change. And so one of the main differences between the 2016 model and the 2019 model versus what was done in 2008 is the plate boundary configuration in the Pacific was updated quite significantly. And so you have huge differences in your mean age of the ocean floor, and that consequently, we've got younger ocean floor. That means we have a shallower depth and then consequently a higher sea level during, say, the Cretaceous. In 2019, which is the most recent plate model, there were some more changes in the Eastern Tethys and the Caribbean. And so consequently, we have a slightly different sea level curve that we would get out just from that. And so this can make a difference of about 50 meters. It could make a much higher difference, but these are all models kind of built upon each other just from what your starting point is. And so once we have whatever plate model we want to use, and I'm going to use 2019 for my basis for the rest of this talk, or for most of this talk, we then have to decide what kind of age depth relationship do you want. So there's quite a number of them. So Parson Slater from the 70s, Stein and Stein, Crosby Mackenzie, and then Richards. There's a lot more, but I don't want to overwhelm you too much with too many lines today. And so if I just take these 4 different oceanic subsidence curves and then apply it to the exact same plate model, I get huge differences in what my depth may have looked like, which has a huge influence on what the sea level may have looked like if you just used basement depth here. So this is like 100-meter difference in the Cretaceous, just based on what my age depth relationship is. And so this creates more uncertainty when we're reconstructing sea level into the past. So we use then look at what our sediment thickness may have done. we have we know that sedimentation is not the same in all ocean basins, or that the amount of sediments, it's not the same in the ocean, all ocean basins, I should say. And so Clint Conrad in 2013 said it's 4 times higher in the Pacific Ocean versus the Indian and Atlantic Oceans. And then he suggested this was largely due to its distance from passive continental margins. And so in 2017, Adriana Dukovic and others, including myself, I guess, we came up with this new model of sediment thickness, and this is based on the age of ocean crust and its mean distance to the nearest passive margin. So it's I guess like a relationship that's derived based on your present day observed sediment thickness, and for like each pixel, it gets the age of the ocean crust and like how far close it is to the nearest passive margin, and calculate some kind of relationship. We can apply this through time. And so you can see, compared to just this is an older version of what the modern day sediment thickness looks like. If we use the relationship from 2008, we have huge amount of sedimentation in the sediment thickness in the Pacific, Western Pacific, which we don't see in the observed. And in the 2017 model, we're missing all of that. But we do get all of that sedimentation along those passive margins in the Atlantic and the Indian Ocean that you can also see in the observed. So it's not an exact match, but it does a much better job than what we used to. And so here again is just an example of what the sediment thickness looks like sometime during the Cenozoic from the 2 different models. And so in the old relationship, we had huge amounts of sedimentation in the Pacific that looks pretty unrealistic, and it completely ignores anything that would have been around a passive margin. Whereas in the newer sediment thickness relationship, we get sedimentation, sediments accumulating along those passive margins, and we're missing all of those, or we have less accumulation of sediments in the Pacific, which is what we would expect. And so if I then look at what sea level may have done based on these 2 different relationships, so here it's kind of like an additive plot, if that makes sense. We've got what you would have had your sea level just as your basement depth, and I can add sediments to that to see where it would get. And so there's not too much difference in the last 50 million years, depending what both sediment thickness relationships do a pretty similar job. But you can see the global relationship really overestimates things in the Triassic and Jurassic. And that's because the Panthalassa, the Paleo-Pacific, dominates reconstructions at that time. And that the 2008 relationships just giving us so much sedimentation in the Pacific that doesn't make conceptual sense, considering it was surrounded by subduction zones and it's just so large. So this takes influences things on the order of 50 meters, and can also have can play a role in what your resulting curve might look like. And so you can also look at the influence of large igneous provinces. And so in 2008, they reconstructed lips. This is Kerguelen Plateau, my favorite lip. And the model that they used to reconstruct them was quite simplistic and basically just got the median depth or median height of the lip. So it compared the depth of the surrounding ocean floor versus the depth on the lip itself, and then got the difference, and it was a flat plateau, tiny bit of filtering applied. And so a lot of the times the way that you calculate your median depth for the surrounding floor, ocean floor, versus your actual lip height, because it's really susceptible to any like abnormal ocean crust, your lips are often underestimated in height, and you're not getting any of that like actual nice topography of the lip that may be important if you actually in the end want paleobathymetry reconstructions. And so we know that the lips are often underestimated in the 2008 model, which means that the contribution to sea level was underestimated. So in my work, we are using a new model based out of the University of Tasmania, one of Joe Whitaker's students, and reconstructing using contours and modifying how it calculates the difference in the 2 like normal ocean floor versus the actual lip. And we find that when we do this in a bit more of a rigorous way, it actually does make quite a bit of a difference in sea level, especially compared to what they got in 2008. So this is also kind of on the order of about 50 meters compared to if you don't have lips. One of the other things that's important to note here is that you can see that, so you can't see it very well, but this without ellipse line actually continues all the way down here into the Triassic and Jurassic. And so one of the huge problems with the large igneous provinces are that we just don't have data of problems for a lot of the Mesozoic. So can't remember off the top of my head, but I think one of the first ones erupts around 154 million years ago. And then you've got a number of lits erupting about 120 million years ago, which is why you're getting this shoot where you can start seeing the difference there. But because we're having to synthetically reconstruct a lot of the ocean floor, especially in the Jurassic and the Triassic, we don't have any information about how we can reconstruct this for this time. And so this is not something that we can actually reconstruct all the way through time and include in our late Mesozoic reconstructions. And so if we go back to that really fast, awful plot that I showed you of all these different sea level curves, and then we add what we've gotten so far. So similar kind of method to what Muller et al. 2008 did, we get this red line. So you can see during the Cenozoic, that's like within the spread of all these other sea level curves. During the Cretaceous, we don't really get a Cretaceous high stand like some of these other ones do. And then we've got a huge drop in sea level in the Jurassic and Triassic, and this looks pretty ridiculous in my opinion. And so, then we can ask ourselves, like, what are we missing? What about those uncertainties inherent in our plate tectonic model? Because we know our plate tectonic models aren't perfect, and we're missing a lot of things. So I thought I'd ask myself a hypothetical, and I want to really emphasize this is not at all what I think that the world looks like. But we know that back arc basins tend to replace areas, or they tend to be in areas that if we didn't have a back arc, we would have had deep ocean crust reconstructing there. So the presence of a back arc tends to increase sea level. And we know that especially during times before the Cenozoic, we're missing back arc basins from our plate model. And so one of the questions I had was, what if we had no back arc basins? So obviously it would be better to go the other way around and add all the back arc basins, but I don't have infinite time in my life. And we don't have geologic evidence for a lot of, we just don't have the geologic data we need to reconstruct these back arcs into plate model for a lot of them. And they're quite time consuming to implement. But it's a lot quicker to just remove them all and pretend that back arc basins just never existed in geology. And so here is what my normal reconstruction looks like. And so I'll show an animation that's a bit more zoomed in a second. But you can see here we've got some deep ocean crust. We've got some old ocean crust, sorry, in the Western Pacific, and then some back arcs near Southeast Asia and Southwest Pacific. And so if I get rid of the back arc basins, all of those back arc basins, instead of having these young spreading centers in Southeast Asia and the Southwestern Pacific, we're actually just getting really old Pacific Ocean crust there instead. And so here's the difference. So you're getting like a difference of 80 million years in some of these areas. And I removed a bunch in the Tethys as well. And so there's not too much of a difference in the Triassic and Jurassic, because there's just not that many back arc basins to remove from the plate model. And so, so here you can see hopefully a bit better. So a bit of a spot the difference, but you can see here, instead of getting all of this this back arc opening, we've got slightly older crust here, and then you'll see really along the Southeast Asia and in the Southwest Pacific, I've just removed all those, deleted all those isochrons that were used for the back arcs, and just extended all of, instead of subducting the Pacific ones, I've just extended them all. So you can see these huge difference in the age here. And so this has a huge difference. This has a huge influence on what sea level may have been. So we compare the mean age. We'll see most of the differences actually in the Cenozoic, because that's when the arcs are that I could remove. And so we see that the mean age of global ocean floor is a bit higher at present day if I had got rid of all of those back arcs, which means our depth is a bit lower. And that means that sea level was almost 150 meters. It would have been 150 meters lower if we had all that ocean crust there. So we know then that if we had a lot of back arc basins, right now we're kind of reconstructing the Mesozoic as this hypothetical back-arc-free world. So if I had the ability to add all of these back-arc basins during that time, maybe, I don't know if it would exactly, but it might be on the order of 50 meters to 70 meters influence on sea level at that time. One of the other things I looked at was passive margin depths. So when we reconstruct the paleobathymetry, traditionally what we've done is we've only ever actually gone to the continental ocean boundaries. So we've only reconstructed the oceanic floor and just ignored anything that was continental. But a lot of these passive margin, we can reconstruct their paleo depths based on their total tectonic subsidence and using uniform extension model. This requires a number of assumptions in the way that I did it, but we've got better ways to do it now. And so we get different, so when I did this a few years ago, we could get two different styles of what paleobathymetry may have looked like based on our a couple of assumptions on crustal thickness and sediment density and stuff like that, and based on the style of sedimentation we tried to implement into the model. And so here's an example of what the passive margin depths look like in some of these areas. So I only reconstructed here modern day passive margins where I had pretty decent constraints. And so you can see we're getting reconstructed material along South America and Africa. You can't really quite see Africa. And so this also then is influencing the area that we're reconstructing and then incorporating into our sea level calculations for when we calculate in volume. And so if I look at the contribution of everything to sea level, so I've shown you this, this red line is what I'm calling the traditional curve, so similar to the components that was used in the 2008 sea level reconstruction. So we've got our basement depth here, sediments has more of an influence in the Cenozoic compared to in earlier times, and here's our lips. So you can see they start, I think there's one, yeah, from 150, but a lot of lips get in place around 120 million years ago, so you can really see that line there. And so if I incorporate some of these like best estimates based on these other components, you know, we can include some of these more extensive area changes because of those passive margins. We can also include, you know, kind of what an estimate for maybe what lips may have been like further back in time, considering it's a pretty even estimate of, you know, pretty even influence of, you know, on the order of 50 meters for when we've got a number of lips. So, and we know we must have had some kind of volcanism and lips back in the past. So let's add that. And then I'll add, you know, just this kind of back-arc basin estimate. This tapers, I think, between like 0 and 120 meters. And it filters depending on what time you're in. And we just add them before the Cenozoic. And so then our resulting curve is what I'm calling a refined curve. It's kind of an extrapolation based on these different components. But we're getting in the Triassic and Jurassic sea level that's, you know, 150 meters different to if we didn't incorporate that kind of thing. And so if we go back to this awful mess of lines, you can see here, there's our red line is this traditional model. And if I add all of these different these estimates, my sea level curve would actually kind of be more in line with where some of these other models, especially those stratigraphic based models, end up with at 150 meters higher compared to there. But we're also getting you know, really high sea level in the Cretaceous, which is probably not realistic at all. And then this is also missing components like dynamic topography and all those kind of things. So I'm not saying this is a realistic curve, but it's just trying to assess what some of these different components may have done. And so I just wanted to really briefly just touch on some of the things I've been doing since this paper was published, is looking at reconstructing paleobathymetry and trying to refine some of those reconstructions, less so for sea level specifically, and more because I'm really interested in paleogeography. And so we've in, you know, I'm calling one of the traditional methods, so similar to what they did in 2008, So going from the age grids to a basement depth and adding components such as sediments, glitz. I also add a whole bunch of seamounts and stuff now for where I have some kind of ages for them. And there's also this pipe backtrack module that we can use to reconstruct preserved crust. So it's a backstripping approach. With a couple of assumptions in it, but you can see that we're reconstructing all of the ocean floor from present day and through time. And so this would also give you a very different kind of sea level curve compared to if you just use the traditional one. I would suspect the backtrack one would be a bit shallower. And so if you want to try it, you can just download the package, I think, off GitHub or with pip. And so here I've just shown you that, but this is what you get straight out of the module. It reconstructs these continental areas as well as the oceanic areas, and you can choose your oceanic subsidence model. So here I've done with Richards et al., but it's also got a few others implemented in it. One of the major assumptions in it is that it just assumes a single lithology for sediments, and it just assumes constant sedimentation. And so we know that's not real, and so or that's not what actually happened. But it allows us to at least start reconstructing paleolithometry on a larger scale. And it also incorporates an offset when you calculate it, so that when you calculate your paleolithometry, the result you get at 0 MA perfectly matches what we have for eTopo. So often there's a few hundred meters difference between the different ocean basins because oceanic subsidence relationships don't aim to perfectly reconstruct everywhere in the world at once. You can also include dynamic topography if you're interested. You still require oceanic paleolithometry reconstructions based on an age grid for all those synthetic areas, which you can see here would be in gray. But yeah, if you have any questions about this, I'm happy to help if you do want to run it. Dima likes to tell me it's a nice one-liner, which I actually hate in Python, but it is there and it will run just on your laptop. And so just as a summary, so we can see that reconstructions of sea level based on ocean basin volume showed large variations. And there's a lot of different decisions that go into how you calculate your ocean basin volume that's also going to influence what those sea level is going to be. And all of those different options that you choose will can have a large influence on your sea level. I really want to emphasize that I don't include everything that influences sea level. I'm not trying to pretend this is a complete and comprehensive sea level curve. And so one of the big things I don't include is mantle-induced derived dynamic topography or water fluxes with the mantle. And there's just huge uncertainties as we go further back in time in what the plate tectonic model itself is doing, and also in how you reconstruct paleolithometry. So always bear that in mind when you're using some of these reconstructions that go further back in time for sea level, especially if they're tectonic derived. If you want to know more, the paper in Science Reviews, or please shoot me an email, ask me questions. I'm always happy to chat. I'm pretty sick of talking to myself all the time. So it's always nice to hear from people. Yeah, and that's it from me.
Hi, Nikki. Great talk. Thank you very much. The question I had was, there's a lot of people in this room who worry about trying to reconstruct, for example, sea level during the Pliocene or last interglacial. It's quite difficult to tell from those plots, but is the amplitude of sea level change over those kind of shorter time periods, so a couple of million, 3 million years, is that large enough that we need to worry about that when we're tying our reconstructed sea levels back to ice volumes? Because if actually the tectonic change in sea level is significant, then maybe we need to take that correction into account as well when we're doing those, trying to tie back our sea level estimates to ice volumes and where it might have come from, whether that's sort of Antarctica or Greenland, for example.
Yeah, so I should have said I assumed an ice-free world for a lot of this. I completely forgot because I always forget that ice exists. But yeah, I don't think off the top of my head that the sea level variations for the Pleistocene or the Pliocene, like the tectonic influence, would have been that significant. But like if you wanted to incorporate something like that, I actually would reconstruct the world using that pie backtracking method, because you're going to get the best model for what bathymetry may have looked like a couple of million years ago compared to like a very uncertain result. Because we know that paleobathymetry at 0 MA doesn't match at all what bathymetry looks like, if that makes sense. Yeah, but I would imagine it wouldn't have a huge influence. There's not really that much that's changed in the plate tectonic model, like in plate tectonics for the last 2 million years. And then the uncertainty of everything, I guess, you know, you could be introducing uncertainty.
Yeah, I think we've got one online question as well.
No, that's actually for myself.
Okay.
Yes. Hi, Nikki. This is Del van der Meer. I'm a great fan of your work and the work of the University of Sydney in general. So in your talk, you're showing the large igneous provinces adding an extra contribution to sea level. And
Yeah.
I was wondering, as you pointed out, that the contribution of the LIPs is actually relatively constant. So I was actually a bit surprised. I was expecting more peaks and troughs in that contribution. So could you explain a little bit more why it's more or less constant in your model?
Yeah, I'm actually not quite sure why it's just completely constant. I think it's partly because just so many lits erupt in the model at 120 million years ago, and we really just incorporate the like those major ones here. So we're not incorporating like any of the seamounts, which we have, you know, more eruptions through time. And because you've just got so many things happening at 120 million years, and then the main ones that erupt and they take up the largest volume, once they're there, like there's not that much else to kind of perturb that line, if that makes sense. If we had a huge amount of eruptions happening at like 60 million years, you'd expect to see a bigger, like another peak then. But I think it's just partly because there's just, yeah, everything at 120 million years. When we also incorporate the lips, there's a couple of ways you can do it. So you can incorporate that like transient uplift of the plume, and then it kind of, so that would mean that your lip is a bit higher and it will subside with crust, but also subside because of the cooling model. And then when you have another lip erupting on top, I guess that would then increase the curve, but just like a little bit if you have like just one more lip afterwards. So it's not like quite a constant contribution because of the lips, depending on how you, what kind of approach you take to reconstructing their heights through time. But yeah, it is surprising that most of them, it's just a kind of constant, almost like looking like a constant line.
Yeah, okay, thank you.
Thank you. We've also got one online question, which is from Neil Hodgson, who says, can you speculate of the effects of dynamic topography on your sea level curve? And he also says, a great talk, by the way.
Yeah, thanks, Neil. I'm a little hesitant to speculate on the effect, just because dynamic topography is a little beyond what I really look at. But there's, yeah, Alex Young has a paper, I think it came out last year or the year before, with some people from Sydney Uni as well, that looks at dynamic topography on sea level specifically. A lot of the dynamic topography models vary in magnitude. And so I guess then it also depends on like which dynamic topography model you use. And so I don't have a particular favorite. So yeah, sorry, I can't really speculate on the amount of, on the influence of it.
Okay, thanks very much, Nikki. So we put Nikki's talk this morning because so she didn't have to talk in the middle of the night. But we're now switching from deeper time back to more recent times with Tasha Barlow, who's going to talk about rates and drivers of last interglacial relative sea level changes in Northwest Europe. Okay.
Thanks, Ed. Right, good morning, everybody. So it's nice to be on this side of the lectern today. So I'm going to kind of, I guess, be a little bit building upon what Alessio was speaking about yesterday, but Alessio was particularly talking about the high stand, which is the focus of the project that he's currently involved in, and the project that we have in Leeds called Riser is particularly looking at rates and ice sheet contribution, as we picked up a little bit in the discussion yesterday afternoon. So this is a sort of bit of a summary of some of the work we've been doing, and I'm stood up here, you know, as the project PI, but it's very important to say that it's not really down to me, most of this work. We've got no pointer. Okay, so yeah, I want to highlight particularly the 4 early career researchers that have been involved in this project. So Victor was working with us before, he's now in Belgium, but Dr. Amy Maguire, Dr. Graham Rush and Oliver Pollard are all here today Amy's particularly responsible for a lot of our chronology work, Graham for the relative sea level reconstruction, and Oliver's PhD is looking at the GIA and ice sheet modelling. So much of what I'm showing today is down to their work. So please do speak to them during the breaks and talk to them about what they're doing. So just to kind of bring us back to the last interglacial, just a little bit of summary in regards to what Alessio spoke to yesterday. There's been a series of estimates as to the nature of the last interglacial sea level high stand. And this is just some of the kind of highlights, I guess, from the literature over the last 10 years or so. And just here on the right, we have the IPCC prediction that Alessio wrote that sentence for. I currently had COVID at that point, so that's entirely down to Alessio, that statement in there. And then also the Dyer plot that it was a little bit kind of lower than some of those global estimates, as Alessio touched on yesterday. But the key question is not just obviously that high stand, which is really important, but also which ice sheets contributed to that to that sea level high stand, and also when, and also how quickly. And there's a series of kind of contesting views on this. So this is a plot that we put together in a paper back in 2019 to just illustrate the differences in the models for the last interglacial Greenland ice sheet minimum. And in red, you can see where the models kind of overlap and there's agreement, and in blue, there's less agreement. Fewer models agree. And there's a sort of general consensus that the Greenland ice sheet may have been smaller during the last interglacial, but by how small? And similarly, similar questions around Antarctica. This is just an illustration. I could have picked any one of a number of models, and there are people in this room who are far more experienced on this, but this is just a plot from Chris Turney to illustrate how Antarctica may have reduced in ice volume during the last interglacial. And if you look at the plot in the top left, you can see quite a spread in that model distribution. So we think that the ice sheets were smaller, but by how much? But I just wanted to highlight this paper that came out last week. It's actually the preprint, so it's not yet gone through peer review, but it's just a really cool study to illustrate that we need to use a range of techniques to identify this problem. So this is actually a study of genomics of a circumantarctic octopus that is found around Antarctica. And by doing detailed genomic studies, the authors have identified that there must have been seaways between the West Antarctic ice sheet open during the last interglacial, because otherwise the genomic structures of these species don't make sense. This idea has been around for a while, but chronology has been an issue. And as far as I'm aware, this is the first time that they've been able to use this. So I think it's just a really cool piece of work. Yes, it's not been peer reviewed, but I encourage people to go and have a look at it. And it really illustrates why we need to bring together a range of techniques to answer these questions. So how does Northwest Europe come into play? So why, if we're caring about Greenland and Antarctica, would we look in Northwest Europe? Well, the reason for that is the sea level fingerprints, the gravitational pattern that occurs as a result of melt of the ice sheets. So these are just some replots that Graham replotted from Carling-Hayes 2014 paper, which are two examples of what happens if West Antarctica melts or if Greenland melts during an interglacial period. So if West Antarctica melts, that gravitational sea level fingerprint means that many of the areas in the northern hemisphere, those shown in the dark red and also in the Indian Ocean, experience sea level rise above the global mean. And the pattern is inverse with respect to Greenland, so that Northwest Europe actually experiences negligible sea level rise should Greenland melt. And it's that sea level fingerprint pattern that we're trying to exploit to understand where the water came from with respect to the last interglacial. Now, this idea has been around for quite a while, but it's quite hard to test. And satellite data is allowing us to do that on recent observational timescales, but it is tricky. And there's a few people in this room that have tried to do this in regards to other periods as well. So if we zoom in on Northwest Europe, this is some plots put together by Jackie Alsterman and her team as part of a paper we currently have in revision. And it's just to illustrate that point further. So this is a scenario of West Antarctic melt, and you can see the oranges suggesting higher sea level rise, whereas by comparison, Northwest Europe experiences negligible sea level rise as a result of Greenland. And the blobs on those plots are a series of data points that come from absolute dated sea level indicators. So by that, I mean basically things that have OSL chronologies with them. And in this area that's kind of limited, this is quite a heavily filtered data set that Rob Barnett put together, and you can see those plots here on the right-hand side, and it includes a new series of data sets from raised beaches in southwest Britain. And by compiling that together and doing Bayesian modeling led by Blake Dyer, we produced an estimate as to the nature of the GIA corrected sea level for Northwest Europe during this time period. So that sea level sits at around 5 to 6 meters above present. Then using similar methodologies as was done in the Dyer 2021 paper, we've tried to come up with an estimate as to the nature of Antarctic contributions to that sea level pattern during the interglacial. And this is the probability distribution for that potential Antarctic contribution during this time period. So about 5 meters of global sea level, plus or minus 5, and interestingly occurring quite early within the interglacial. So I kind of, based upon this relatively limited data set, focusing just on the absolute data points and the sea level high stand, we suggest an early Antarctic contribution with probably a later Greenlandic contribution to the interglacial sea level. But that again is really focusing on the high stand. And the question we're trying to answer in the RISER project is constraining rates. Alessio mentioned the Wallace database yesterday, and this is our contribution to Wallace, which is the Northwest European data sets being put together. And you can see, in fact, if you look at these, all these yellow and green and orange blobs in here, there's a lot more data points than is selectively included in the Barnett paper, including, in fact, a data point here from Trafalgar Square, which is literally within half a mile of where we're currently stood. Hippos once roamed the estuarine environment of Piccadilly back in the last interglacial. The challenge here, though, is that many of the chronologies are relative, and Amy could spend hours talking to you about this, and happily will do. And that's quite hard to be able to tie some of these things together, say to be able to compare that Thames data point with data sets in the Netherlands. So that's why those records are not included in the Barnett analysis, but it's something that we're currently working on to try and build that compilation together. The other thing we're doing is collecting new data points to allow us to establish new sea level reconstructions that allow us to try and understand rates. And the reason this has become possible is not only that wealth of information providing that research framework, but also the growth in offshore wind. I think those of you who know me know that we've been working with offshore wind data sets now for the last 5 or 6 years, but particularly within the RISER project, they've allowed us to target offshore landscapes that were once freshwater peatlands containing things like hippos that were subsequently transgressed due to flooding of the North Sea. This is Victor's work when he was with us in Leeds, and he mapped out from a series of wind farms, but this is one wind farm off the coast of the Netherlands, how that landscape may have looked. And in the grey, browny colours here is that the representation of that terrestrial landscape. It's what's preserved. Admittedly, there almost certainly is erosion. And we can then use that map to try and understand the coastal geomorphology over time. So we were very fortunate in 2020 to collect 5 new cores. I was the chief scientist from my lockdown spare room, which was a very weird position to be in, but it was a successful cruise, and we had 5 new cores to allow us to try and to tackle some of these questions. It's proving tricky, I'm not going to lie. We are lacking diatoms and foraminifera, which is really the kind of crux of many of the sea level reconstruction methods that I have used over the last 15, 20 years or so. So we're having to look at things a little bit differently. We're using things like geochemistry and also the biomarker work that Martina Conti leads on, and she has a poster about, she mentioned yesterday, along with detailed sedimentology and also molluscan records with our colleagues from the Netherlands to understand the nature of those transgressive surfaces. We predate radiocarbon, but we're in that sort of tricky window where other things don't necessarily work as well. So we have got some OSL ages. They're interesting in the moment, and we are retargeting those. Amy's working very extensively on the relative chronology of the biostratigraphy, along with the amino acid dating techniques is something we're looking at with the University of York group. Also excitingly, and I apologize, we need to take some higher resolution photos of these. We found what looks to be the first occurrence of tephras from the last interglacial in the southern North Sea. These are currently being analysed from the University of Cambridge, and this is work that a master student of ours, Megan Edwards, has done. And we're just starting literally next week a new tephra chronology element to this work as well. So I guess the slightly kind of disappointing is I don't necessarily have the answers because, you know, it is ongoing, but this is kind of our summary of the situation. And there are question marks here for good reason. We think, and this is an example of one of our 5 cores, we have flooding recorded of the last interglacial North Sea as transgression of our freshwater peats. But also interestingly, in each core we find, well, not in every core, but in most of our sites, we find at least 2 peaks. And we knew that when we cored. Victor's geophysical work that demonstrated that point. Potentially interestingly, though, we possibly have also records of flooding of the last interglacial marine isotope stage 7. So the preceding interglacial again. But as I said, that's work that's ongoing. So this is our reconstruction of the paleogeography of the Dutch coast during that time, based on the geophysical work that we've done. And you can see this is the wind farm area here in red, this coastal plain that formed during that last interglacial period. In orange is our deepest core, where we have our lowest transgressive sea level index point, and in yellow is our uppermost core. And so our kind of simple summary at the moment is that we have evidence of probably at least 10 meters of sea level rise, but in how long is still the unknown. And, you know, it was mentioned yesterday by Sophie, clickbait. Well, we hope to try and have some answers by the INCWA Congress in Rome in July, but we would guess within a millennia or two. That's our current working hypothesis. So a reasonable amount of sea level rise. And also, when you look that this distance is only about 20 kilometers apart, that can't be due to differential solid earth displacement. That is due to ongoing sea level rise. We are going to correct for the GIA, and I'm going to talk about that in a second, but this is almost certainly due to either the barostatic or eustatic component that occurred during that time. So just to move on for the final part of my talk is to focus on the work that Oliver's been doing in his PhD. And that's because glacial isostatic adjustment is an important part of the uncertainties that we need to consider, whether that be reconstructing sea level regionally within the North Sea or consideration of the global mean high stand. This is just to illustrate that point. This was a paper now from a few years ago from Denby et al., which just illustrates nicely the variation that you can sort of put into the model in regards to the preceding glacial maximum, so marine isotope stage 6 glaciation, and the implications for sea level curves. In this case, far-field sites in the Seychelles and Bermuda, the nature of the sea level high stand that occurred during the interglacial is highly dependent on the nature of the preceding glacial maximum. This is the work that then Oliver's exploring in his PhD. And because we are working within an area that's close to the ice sheet, obviously this has even more implications. So the last glacial maximum ice sheet history of Eurasia is pretty well constrained. You know, we have a lot of chronologies here, and the databasing work by people such as Anna Hughes has been amazing to be able to understand that. By comparison, of course, understanding any preceding glacial is a challenge. And we can see here in green, Christine Batchelor's reconstructions with the uncertainties Oliver's plotted up, and compare that to the last glacial maximum line in orange. And just for illustration, 2 plots here of last glacial maximum reconstructions from I6G and from GLAC1D for Eurasia, and then Flo's model up here for the PGM and Kurt Lambeck's model. And you can see straight away quite a lot of differences. So it's not appropriate to be using reconstructions from the last glacial maximum to try and understand sea level during the last interglacial. So what Oliver's been doing is developing an ice sheet model using Evan Gowen's ice sheet model framework, which requires an ice sheet margin input. So in this case, Christine Batchelor's ice sheet margins, a shear stress map, which controls the basal sliding characteristics, and then also a regional topography that requires correction for glacial isostatic adjustment. Now that one figure summarizes 2 years of Oliver's PhD, and instead of me trying to capture it all, I'd encourage you to look at the paper that's currently under discussion in Cryosphere, because there's a lot of work that's gone into that, in particular the work that Oliver's been doing to quantify the uncertainty associated with it. But the take-home message is really these figures here. So Oliver did a 200 ensemble member run to look at this, but this is the reconstruction from the mean ensemble member for the Eurasian ice sheet during the PGM. And it has a sea level equivalent ice sheet volume of about 51 meters, which when we then compare that with the distribution of the models that have been published previously, in the dark green at the bottom here is Oliver's ice sheet volumes once he's conducted a history matching exercise. It's quite similar with its sort of peak distribution with the Lambeck model. Flo's model sits quite a lot higher in terms of ice sheet volume equivalent, sea level equivalent, apologies, and the Bass de Boer reconstruction sits below. The orange here is the comparison for the volumes for the last glacial maximum. So This uncertainty here in the volume is obviously key because that has importance in regards to understanding the glacial isostatic adjustment. So just to kind of finish off, the next stage that Oliver's doing is inputting that ice sheet model into a GIA model. This is in association with Natalia Gomez. The ice sheet modeling, I should say, is done with Laurent Gregoire. And this is just one illustration as to the nature of the GIA response to that ice sheet load. Obviously, we'd expect maximum vertical displacement under the thickest part of the ice sheet. And then in orange is all of these dots here are the data points from the Wallace database from both our compilation and contribution to it and Evan Gowen's contribution for the northern part of Europe and Russia. And what Oliver's currently working on is exploring the sensitivity to that ice sheet volume changes, but also the sensitivity in regards to the different elements of the GIA model. So 4 just illustrative sites here. If I look at the ones for our site in the Netherlands, where our new cores are collected, in orange is the sensitivity for the sea level over the interglacial to the volume of the ice sheet. And in fact, you can see that's pretty small. The GIA outputs don't really care about the ice sheet volume significantly. But by comparison, they do care more about the timing of the deglaciation, so how quickly the ice was lost, and also the response to the Earth model. And the Earth model input looks to be very key in understanding the range and that distribution of spatial pattern to the relative sea level. And this is work that's currently ongoing, and I encourage you to speak to Oliver during the rest of the day if you want to understand more. So to summarize, during the last interglacial, global mean sea level was at or above present. There has been some variations and some possibly lowering of that high stand estimate, as Alessio picked up on yesterday. The work that we've done in the paper that's currently in revision by Rob Barnett suggests potentially asynchronous ice loss with an early Southern Hemisphere contribution and a later Greenland contribution. And I think really my gut instinct suggests that we have a range of evidence pointing towards that type of scenario. And as Alessio mentioned yesterday, we're starting to now consider this on a more global analysis. It is key to be able to understand rates. And some of us were at the World Climate Research Programme conference in Singapore in the summer, where we had a range of practitioners also present. And really, it's rates that people want to know. They need to know how quickly things are going to happen, because that determines the nature of your response. How high it's going to get is important, but how quickly do we need to be able to respond? And I'm sure speakers this afternoon who are looking at more current futures and future sea level will speak to that further. Northwest Europe provides us with an important context to be able to identify the patterns and rates of sea level change. And we're also undertaking some kind of innovative approaches to looking at uncertainty in ice sheet volume and GIA to better understand last interglacial sea level. Thank you very much.
That was a really fascinating talk. Thank you, Tasha. Just a quick query about the actual global mean sea level, I suppose.
Yep.
We've talked about the IPCC previously saying 5 to 10 meters. Alessio's inferred it might be close to 5, and now you're suggesting at or above. Would you be willing to hazard a guess at to where you feel, if you can put a number on it in terms of global sea level, where are we looking at a higher rate, or are you potentially saying it is actually close to where we are now?
No, I think we're looking more at that kind of 5 meter level, plus or minus what, I'm not quite sure, but I think what the evidence we have and the evidence through the PALC community more broadly, and I think Alessio and I, very much represent a research that's ongoing by a huge number of people, which just happens to be us that stands at the front. I would suggest we're kind of looking at that 5 meter. I think the sort of 10 plus meters that had in the past been suggested, I think largely people are suggesting that's not the case. Now, there's plenty of people ongoing to look at direct evidence from the ice sheets, and I know Tina's going to talk a bit about that next. And that's going to be important to try and to really pin that down as well.
Okay, thanks. So next we have Tina van der Vleut, who is going to talk about some of those potential direct sources of evidence from the ice sheet.
Thanks, Ed, and good morning, everybody. So I'm going to give a slightly different talk now. So I will talk about a project which is just about to kick off, a big international project about the sensitivity of the Western Arctic ice sheet to 2 degrees warming. And it's really about getting like 2 new sediment records from a place in Antarctica where we really ought to be looking. And as always with this project, there's years of work going into it. There's a huge international team behind it. So I just listed at the top here the chief scientists of the project, which are Richard Levy, myself, Molly Patterson, and Hugh Hogan, and Denise Kulhanek is the staff scientist. But I want to get us kind of started from the beginning, and we talked yesterday about how we communicate to the public as well about kind of sea level rise and the different dimensions. And I always find, as we think about warming of our planet and, you know, what the consequences are, you know, it's important to say, well, ice is melting, and it's important that that is something we can see and we can feel and people can experience. And the most visual way to do that is always to look at the mountain glaciers. But everybody in the room here knows that the big kind of factor in the sea level equation is, of course, our ice sheet. So we have about 7 meters tied up in Greenland. We have about 57 meters in Antarctica. Petitioned in the smaller Western Arctic ice sheet was 4 meters and 53 meters in Eastern Antarctica. So when we look at the recent IPCC report, I think they did a stunning job, and I know people in the audience have been involved with this to kind of integrate paleoclimate records throughout. So when we look into the future along these socioeconomic pathways and look at, like, you know, the range of 1.4 to 4.4 warming projected for the year 2100, that equates to sea level rise between 20 centimeters and a meter or so. But what I think is really important is the lower panel here, and this is really from the summary for policymakers, and I'm sure that made it in there, which shows the stippled line here. And that stippled line is what they call the low likelihood, high impact storyline. And that includes ice sheet instability. So some of these processes Carrie alluded to yesterday, which would actually get us to 2 meters sea level rise by the end of this century. And then if you look at the vertical column here, it makes the point that there's a lot of commitment we have to think about, and that matters as well. So if we look at the year 2300, we are looking at 3 to 7 meters with kind of a level of 15 meters that can't be excluded. So the sea level is a slow response to the warming we're seeing, and I think that's something important. And, you know, Natasha said, like, it's the tipping points and rates we really have to wonder about. And the reality is there's lots of work left to be done. So when we put it into the context of the Paris Agreement, you know, we of course aim to keep temperatures below 2 degrees, ideally at 1.5. Well, this is the reality where we currently sit with policies and actions. We are on track for 2.7 degrees warming. There's lots of kind of good promises to get better, but, you know, we're not there yet. So arguably the temperature range to look at is kind of between 1 and 3 degrees warming here. And I put on the left our paleoclimate analogs, and we've heard loads about them. So I'm going to focus in on the last interglacial as well. So 5 to 10 meters, the IPCC range, 1 to 5 meters, the kind of newer estimate from Thaya we heard about. And then the Pliocene here, if we don't manage to stay below 2 degrees, we of course look at the Pliocene world, was probably 10 to 20 meters of sea level rise. So Natasha kind of explained it very well, why it matters, you know, to look actually at where the ice is coming from. Sea level rise will not be globally uniform. It really matters where ice is coming from, whether it's in a 1, 2, or 3 degree warming world. And so we really need to look at the potential source. And the one I'm going to focus on here is Antarctica. So again, when we look at Antarctica, the vulnerable parts of the Antarctic ice sheets are the marine-based portions of that ice sheet. You can see on the left here, satellite observations, the GRACE data showing the current ice melting, which of course has a massive hotspot in Western Antarctica. There is some evolving hotspots in Eastern Antarctica. Those of you who know my work know that I'm really interested in those as well, but we'll stay with Western Antarctica today. The attribution is that we have warm waters upwelling on the shelf there, which help eat up the ice sheet from below, basically. And that links into the marine ice sheet instability. So if you have an ice sheet rested on bedrock below sea level, and particularly when it's on a retrograde slope, you can get like tipping points, which lead to very rapid retreat and collapse of big portions of the ice sheets. Geology matters in all of this. We are at the Geological Society. So this is a kind of illustration of the bed elevation. So what the bedrock looks like when you remove the ice on Antarctica. And all the blue areas are marine-based areas. So you can see Western Antarctica is big kind of marine-based ice sheet. But again, there's big parts in Eastern Antarctica as well. So I want to zoom in on Western Antarctica now and do a tiny bit of history. So there was a paper in 1978 already by Mercer, and many of you will be familiar with it, which basically stated that as we rise CO2 and warm kind of planet, the Western Arctic ice sheet may collapse. So that kind of idea has been out there for a long, long time. The point is now, how do we do with observational evidence for that? And the answer is we're doing actually really poorly. So in terms of evidence for collapse, there was a paper in the late 90s, which found some kind of diatoms, some beryllium-10 evidence under one of the ice streams saying, there probably was a collapse at some point in the Pleistocene. There's other work based on the Andril core, which stated there were at least 7 fluctuations between ground and a floating ice in the Ross Sea at some point, but that is not really pinning it down. So we just have to, as a community, say that more than 40 years after formulating an hypothesis, we still don't have any direct evidence for Western Arctic ice sheet collapse in the late Pleistocene or during the last interglacial. And like Natasha, I want to show you just some random snapshots of model outputs here for the last interglacial. You can see on the left-hand side the Conto et al. Kind of work, including the marine ice sheet instability and the marine ice cliff instability as well, showing an open seaway across Western Arctica. In the middle here is a model output which shows you lose ice in the Ross Sea, open a seaway up here. And then on the right-hand side, you can see a model which gives like a retreat in the Amundsen Sea area, but not a lot happening in the Ross Sea. So did the waves collapse? Was there partial collapse? What did the buttressing ice shelf do? We really don't know the answer to that fully. And this star marks the location of where we're going to drill. And I think it becomes quite obvious when you look at these figures why that is a golden opportunity. And before I'm going to kind of talk more about the project, Natasha pipped me to it. Here's the octopus. So this is my pitch of why it matters to kind of go to meetings like this. I didn't know about the octopus paper. It's really cool. So Natasha explained it already. And here's kind of the title. As she said, it's on a preprint server right now. And it's really cool and may provide genomic evidence for Western Arctic ice sheet collapse during the last interglacial. But after reading the octopus paper yesterday night, I went back to look at my departmental emails, and that kind of reminded me of a different world and made me actually ask ChatGPT about like, what does it think? So ChatGPT, for those who don't know, everybody who teaches knows by now what this is. It's an artificial intelligence powered chatbot. You can ask any questions, it gives you an answer, and stunningly good answers very often. So I asked it, when did the Western Arctic ice sheet last collapse? So I asked that. ChatGPT said the most recent collapse of the Western Arctic ice sheet occurred about 10,000 years ago. And I was like, you have no clue. So there's things why we still have to do science and go out there and do observations. So that gets me to the project and what we call the discovery for our lifetime, the Space to Sea project. It's about the sensitivity of the Western Arctic ice sheet to 2 degrees C. So let me introduce the project. So what we want to do is we want to drill 2 long, up to 200-meter long sediment cores from below the eastern Ross ice shelf to unravel the Western Arctic ice sheet history. So we want to drill at the location where the seaway would have opened if it opened. We'll use a novel drilling system, and I'll show you some pictures of that developed in New Zealand. And that is a huge kind of international group of people. We are more than 100 researchers, including 25 early career scientists as well, 35 research organizations, and the international consortium involves 10 nations. So all of this has been made possible by funding. ICDP is kind of funding the operational costs at a significant proportion, but there's national funding agencies, organizations, and institutions shipping in as well, and you can see them all listed down here. So what we're trying to achieve here? Well, we want to actually kind of bring that vision of IODP and ICDP combined words to fruition to get one of these land to sea transects. So if you just kind of pick one of these little Antarcticas here, the point A and the point over here, these are recent IODP expeditions which happened in 2018 and 2019, where there is prior Pleistocene records that have been drilled. The gray point here is the Andril site, which was drilled more than 10 years ago. And the red point is where we are going to drill. So you can see how that is actually going to form a transect. Ideally, one day we want to have a record in the Weddell Sea as well to really get the full kind of picture around Western Arctica. But it's going to be two records, but it's going to like live in the context of a lot of other work as well. So what are the two records? So the first one is the Camp ice stream drill site. So that's the one up here, close to the Cyprus coast. So it's close to the grounding line of the Camp ice stream. It's an area where the ice shelf is 590 meters thick. The ocean cavity below it, and the ISA cavity is about 30 meters. And then we're going to drill into Lake Coturti and Upper Neogene sediments. Of course, beautiful glacial interglacial cycles, no question. And you could see that in the seismics, like we all know, seismics never lie when you drill. So there's kind of our sleeve floor here. We have this big kind of upper unit, which we assume is kind of Pleistocene, nicely layered sediments. And then we have Horizon D, which is kind of a regional reflector, which is probably the M2 glacial and the Pliocene. So we have, with 200 meters, the chance to get into the warm Pliocene here as well. So excitingly, we're going to start drilling this year. So it's going to happen. 23, 24 is the drill season. So November to February next year. Co-chief scientists for BISLAC will be Richard Levy and myself, and the staff scientist will be Denise Kulhane. The second site is the Quarry Ice Rise. So that's the one slightly over here. So that kind of is a location where the Ross ice shelf is grounded. The ice shelf is 516 meters thick, so there's no cavity. When you look at the seismics here, we have what is most likely a Holocene grounding zone wedge in the upper part. And then we get into kind of deeper strata. We say Upper Neogene, probably older, Miocene, Oligocene is kind of what we are thinking at the moment. So that's going to be drilled in 24, 25. Co-chief scientists will be Molly Patterson and Hugh Horgan. I should give a good big shout out here to the operation parties implementing the project. There's been a lot of kind of very sophisticated engineering going on, led by GNS Science and by Victoria University. So there's a team of engineers which have developed a brand new intermediate depth geological drill system, which is capable of working in a combined ice and water thickness of up to 1,000 meters to then obtain sediment cores up to 200 meters long. The two people here in the picture, Darcy Mandino and Alex Pine, are other real heroes. And that is a picture of the drill system at the manufacturer's side. And you can find more information on this on the Antarctic Science Platform website. So this is what the hot water drill system looks like. So obviously we have to blast the holes through the ice shelf first. This is a system which has been designed based on kind of what BAS has been doing. The holes through the ice will be about 30 centimeters in diameter, allowing access to the seafloor. And it has been used and deployed in the field multiple times. And is actually at the moment at the site already. The coursing is the new sediment coring system, which then will be integrated. That's called 8. So it's an Antarctic intermediate depth sediment drill. It's a diamond coring system, lightweight, Seawater drill string. It has a bottom hole assembly with hydraulic piston coring, push coring, and rotary coring. So 3 different setups. For all of you used to IODP cores, we'll get like 4 to 5 centimeters in diameter. So we're not going to get tons of material, but it will be very precious material. The key thing about this system is that it's a lot more lightweight than previous systems were. So it's about 30 tons. I think that compares to the 200 tons or so the Andrill system was, which allows us to traverse the system across the ice shelf to the site. And again, a safe route has been established in previous seasons. And the system, excitingly, is currently en route to New Zealand, to Antarctica. So it left New Zealand. So it's kind of on its way now. So this kind of cartoon summarizes our approach. We'll kind of have our drill system on the ice shelf here. There's kind of our lovely tent village where we'll be living for 2 months, 3 months, some of us. And then kind of tents for operations. We'll kind of have the hot water holes through the ice, put a sea riser in the cavity, and then we get into our beautifully glacial interglacial sequence. And I think a key thing to say here is no matter what we get, the observations we'll make will tell us something we never knew before, no matter what, because the sediments, just by looking at, just by doing the observations, will tell us whether we are under an ice shelf, whether we're under grounded ice, or whether we're in open ocean conditions. So just having the observation at the key location is going to really help us. In terms of our science objectives, well, there's a bit of everything in there for everybody. There's Holocene targets, there's Pliocene targets, there's, of course, late Quaternary targets. There's kind of at the query side, late Oligocene to Miocene targets, and we do a bit of microbiology as well to look at life beneath the sea surface. And everybody who's interested in the details, Molly Patterson kind of a nice kind of article which summarizes this all in Scientific Drilling, which is open access as well, and was published last year. As there's only going to be very few people, scientists, who can actually go to the ice, we are, frankly, not that important. It's the engineers which matter once we are out there. All the science party will get together afterwards when the cores come back to New Zealand. We'll meet in Dunedin at the Otago Core Repository and have a kind of IODP style sampling party. We'll kind of describe all the cores, do all the scanning, and get our samples. So that's going to happen a few months after the drill season has been completed. And I want to, for the first time, introduce our UK team here for Sways to Sea. So thanks to like a special call put out by UKRI, we have a team here of PIs which are associated with the project now, and there will be lots of opportunities for others to get involved. So Ed and I co-led the effort. We've been involved from the early days in writing the ICDP proposal. So I'm going to be the geology data lead and Ed is the modeling lead. I have a poster allowed. I had a poster not about Sways to Sea, but about something else. I'm going to be co-chief scientist for the camp drilling season as well. But because I will be busy with kind of doing the international coordination as well, the key kind of person to look out for is Jim Marshall, who was mentioned a couple of times yesterday. Jim wave, he's actually here today. So if you want to know anything about science, we do kind of for all of this talk to Jim. He has 2 posters. I only introduced one yesterday, so there's another one today. And the rest of our team are Matt Fox from UCL, James Smith from Bass, Lou Syme from Bass, and Lauren Gregoire from Leeds. And our project partners are Mike Bentley and Robin Swiss. And again, ICDP kind of shipped into this as well. But this is kind of our UK component. As you can see, there's a lot of plus postdocs. The project will only kick off from the UK side January next year. So there may be good opportunities coming up for early career scientists as well. So I want to finish with this slide with the excitement that we actually launched a website last week. So there it is, sways2sea.aq. We are present on social media also since last week now, and there's a quarterly newsletter planned. Everybody can sign up for it on the website so you can stay up to date with what happens in the project, which I really hope and believe will be the discovery for our lifetime. Thank you.
Okay, thanks everyone. Can we carry on with our next talk, please? So we're next going to hear from Sarah Bradley, who's our next invited speaker, who's based at the University of Sheffield, and she's going to talk about quaternary sea level ice sheets and glacial-isostatic adjustment models.
I'm just hoping my screen shared, so if it hasn't, then someone shout loudly. So thanks for inviting me to give a talk from the far distant future of Sheffield. So my talk is a bit vague: quaternary sea levels and ice sheets, glacial isostatic adjustments. So I'll just get in with going. So I wanted to start off with sort of a bit of a background on how we make input ice sheet reconstructions for a glacial isostatic adjustment model. And this is this diagram from Pippa Whitehouse's paper in 2018. And you have this idea that you make an input ice sheet reconstruction, such as Cash had said for Ollie's work. You make up an Earth model, you put it into a GIA model, and you make some predictions of relative sea level, you compare them to your sea level data, and you go round and round in this sort of iterative process. But the problem is that your ice sheet reconstruction is then tuned to your relative sea level data, which is then used to tell information about the sea level. So it kind of becomes a bit of a non-uniqueness problem. So there's been sort of other ways of making an input ice sheet reconstruction, such as the very great work by Ollie that I'll mention again, because I like Ollie's work. You can also take output from an ice sheet model, such as Joseph Kusch had done, or you can kind of, which I did many years ago in my PhD quite badly, you sort of guess some ideas where the ice sheet is, but again, make a prediction of the relative sea level, compare it to the sea level data, and you go round and round in this non-uniqueness sort of set. So I wanted to talk about the approach we did in BritIce Chrono and this sort of a hybrid method, which has also been published by Evan Gowan. So as Kasia said, to make an ice sheet reconstruction for a GIA model, you kind of, it's, there's not a lot of information you need. You can break it down into 3 things. You need to know where the ice sheet was, where did it shrink from, when it got there, and how thick it was. So the Brit Ice Chrono project produced this huge database of data to tell us where and when the British and Irish ice sheet and North Sea ice sheet was during the last glacial maximum to present day. And that's what I'm going to sort of quickly overcap today. So Kasia's kind of already said why Britain's great, but I wanted to say why Northwest Europe and Britain's good for a sort of LGM perspective. So this is a map of relative sea level at 15,000 years ago, and you can kind of just make out the coast of Scotland, and all these little brown dots are sea level index points. And 15,000 years ago, there's nothing amazing about this. You have a positive sea level across Scotland where the ice sheet was, and it's fallen along the southern margin. But what's interesting about Britain and the southern coast, as Tasha said, is what's driving this sea level, because not only is there a part of this signal from the British ice sheet, you can also find information about North America and Antarctica. And that's good because, I don't know, Cornwall's a lot nearer than, say, the coast of Antarctica, theoretically, unless, of course, you're getting on a British train. So if you look at a sea level data site in the middle of Britain or Scotland, say, for instance, Forth Valley, this is a plot of relative sea level against time from 26,000 to present. And this blue line is your typical predicted relative sea level that you would get in your site, whereas the ice sheet grows, you reach a maximum of 80 meters above present, and then you fall. But this signal is composed of a large signal from the British and Irish ice sheet, over 160 meters, but nearly an equal but opposite amount from North American ice sheet. As you can see, the North American contributes about 60 meters, and a very small amount from Antarctica. So to unravel this relative sea level across the British Isles, you need to know not only really well what the British and Irish ice sheet's doing, you also need to know really well what the Antarctic ice sheet and the North American ice sheet is doing. But then if you look at data from the southern UK, and similar to what Tasha's been doing over the North Sea, and here you've got your relative sea level signal from about minus 100 meters up to present, your nice steady rise. You have most of this signal is due to the North American ice sheet. So if you look at sea level data around the southern coast of the UK, most of that signal is going to be coming from North America. So if I want to unravel the signal around the British Isles, I need to know really well the British, the North American, and the Antarctica. And this is what we did in the Brit Ice Chrono project. We thought, well, if we can make a really good guess of the British and Irish ice sheet, independent of the sea level, then we can answer some questions about North America and present day sea level change. So not me, because I don't like to leave my house and collect data. The people in the Brit Ice Chrono project went and collected all these cores and got all this new data. It's got this fantastic database of when the ice sheet was somewhere and what it was doing there. So we had a good idea on when the ice sheet was there. Jeremy and Chris kind of produced this nice little sort of, which is not playing. Chris Clark in 2022 produced, just sort of come out, the final reconstruction from the Brit Ice Chrono project, where they produced a set of reconstructions from the geomorphology of where the ice sheet was and how it deglaciated. You can see it here between the pale grey and the dark grey, but rather than just this is the ice sheet final answer, they produced a minimum, maximum, and an optimum reconstruction. And what's cool is you have 3 or 4 different reconstructions of how the ice sheet grew across the North Sea, because we still don't know. Did it grow and coalesce really early at 26,000? Did it have a late coalescence when they joined at the southern margin, then expanded to the north? We don't really know. But at least this way, we had an idea of what the ice sheet was doing, possible set of reconstructions that weren't constrained on the sea level, to kind of get away from this make an ice sheet, make a prediction, change the ice sheet, make a prediction. So this is what I started with. I had all this information, but the problem was I still didn't have any idea about how thick the ice sheet was. So then this comes into this nice model that Evan Gowan published in 2016 called Ice Sheet 1.0. Yeah, it's another ice sheet. So it's a plastic ice sheet reconstruction, which Tasha mentioned that Ollie spent years doing. So we took these margins that I just showed that little movie of, and we said, well, we're going to produce 7 possible reconstructions of how thick the ice sheet was and how it glaciated over the North Sea to kind of encompass some of this unknown that we don't know. So we know the timings, we know the reconstruction, but we don't really know how thick it was. But thick makes it sound like we took the ice sheet and we went it from being 1,000 meters thick to 2,000 meters thick. What we actually did was it was more slightly varying the configuration of the ice divides across northwest Scotland. So rather than kind of saying, I'm going to thin my ice sheet by 30% or 40%, to kind of slightly capture the sea level signal, we had to shift the ice divide. So we produced 7 reconstruction, changing the thickness in the North Sea. Now, this is a lot of information on this slide, so I'll just try and go through it slowly. So because the relative sea level signal across Britain is really spatially variable, if you just kind of take all the sea level data and clump it all together and try and do some statistical fit, you get a really small number, but you're kind of just averaging it by the fact that there's loads of data in the southern margin and not a lot of younger data. So we split all the data up into these kind of 7 little coloured boxes and sort of said, well, we've got 7 reconstructions. How does the model perform in each of our regions when we kind of varied thickness and style of coalescence across the North Sea? There's a lot of big colours and variation. The key point is to basically take away of, we produced 7 reconstructions. They all perform really well, and they perform just as well as my PhD in 2011. So you might think, well, that was a load of 10 years of pointless work that you did there on the Brit Ice Chrono project or something. But the PhD work that I did in 2011 captured the relative sea level data across the UK, fantastic. But the problem was the ice sheet was made of garbage. So none of the information to make the ice sheet and what it was based on was necessarily true. So then you have the problem that you can make an ice sheet reconstruction and it can fit the sea level perfectly. But now when new evidence come along, you go, well, the ice sheet is actually wrong. Whereas now we have an ice sheet that's based on science and new evidence and fits the relative sea level. So if anybody wants to look into the detail of my dots, that's fine. So plus we're a talk on sea level and everybody loves sea level data. These are the 3 sites that are often mentioned: Arisaig, Kintyre and Forth Valley. So Arisaig is up here in the northwest, and then you've got Kintyre, central west, and Forth Valley in the middle. And the Arisaig site, you've got relative sea level in the y-axis and age on the left, and all the little blue crosses are your sea level. So these hybrid, thick and thin, the red, the grey and the black, are our span of thicknesses for the reconstructions for one possible North Sea glaciation. And it sounds like thick and thin, like it's massively thicker and thinner. It's not really, it's just slightly shifting. The movie won't play because Zoom hates me. It's just slightly shifting the configuration of the ice divide to kind of capture the sea level at Arisaig and capture the sea level at Kintyre. Because initially we had this really thick ice lobe across the northwest coast of Scotland, which captured this lovely sea level signal, as you can see here at Arisaig, but the ice sheet signal was massively too thick at Kintyre and Forth Valley. So at this point, we had to do a slight tweaking of the sea level to capture the signal around this northwest coast. And this was our hybrid model where we just shifted the ice divides. But I suppose the main point was to say, we've made a range of ice sheet reconstructions. They aren't heavily tuned to the sea level, and they capture the sea level information for the right reasons. So that's that. So then if I've made this fantastic Brit Ice reconstruction, I say it was me and a lot of people in the Brit Ice Chrono project. I said at the beginning that if you have a really good British and Irish ice sheet, you can then tease out information about North America and Antarctica. So I'm going to quickly mention that. And then because the panel session later on in the session is the paleo relevant for the future, I just thought I'd go over a few little studies we've done where we've used this better British and Irish ice sheet reconstruction to tell us something about future sea level or the future situation. So there's a lot on this graph. So as I said, this data from the southern UK is mostly driven by the North American and Antarctic ice sheets. So we split the data into clusters on the southwest and clusters on the southeast, and separated the data into bins, 4,000 to 5,000 years, 5 to 6, 6 to 7, 7 to 8. So just think clusters of age, that's not rocket science. And then said, how large is the misfit between our predictions and our observed data for a selection of different models? So say, for instance, we have the southeast data here. We take this Bradley global ice sheet reconstruction that I used for my PhD, that's really, really old. And we say, how well does this capture the southern sea level data? Well, as you can see by these massive red error bars here, it does a really bad job, and that's fine because it's old. So then you say, look at the ICE5G model, and you compare this to the GLAC1D model. And the idea of comparing the brown line and the gray error bars is to say, okay, if I alter the North American ice sheet reconstruction, whether I use this published model of ICE5G or a GLAC1D, I'm not saying that one's better or worse. I just have two different North American reconstructions. Can I use the southern sea level data from the UK to tell me something, or is it not sensitive? So you find that at most sea level sites in these little bins, the data prefers the GLAC1D North American ice sheet reconstructions. That just says it's very sensitive to that. The main difference between the North American ice sheet of GLAC1D and ICE5G is just the timing in the North American ice deglaciation. So I've looked at my southern UK data. I've said, is it sensitive to what happens in North American? Yes. Can it make some suggestions about the timings? Yes. So then we looked at kind of Antarctica. So we've got ICE5G and ICE6G. I'm not saying that these are good or bad Antarctic ice sheet reconstructions. I'm just saying ICE5G has a really big Antarctica and ICE6G has a small Antarctica. And that was all we're looking at. And you say, okay, is the data sensitive, or can it detect any of these differences in what's happening in Antarctica? So you look at the gray bar and you say, okay, southeast data, how big's my mean residual? Change the Antarctica, does it really make any difference? So we found that most of the signal around the southern coast, it didn't care about Antarctica. Big Antarctica, small Antarctica, late deglaciation of Antarctica, it wasn't making any difference to capturing the sea level signal. Most of the signal was due to North America. So that's that. It's maybe a bit fast. So as we're talking about future sea level, this was some work that the Brit Ice Chronos stuff went into, looking into future sea level projections. So Matt Palmer and a load of other people published in 2018 the UKCP18 marine report looking into future climate change. I think Ivan maybe will do a much fuller description of future sea level change around the UK. So they took these three different parts to make projections of future sea level around the UK. And GIA models and vertical land motion was just one component that went in to these predictions. So the reason I'm going to mention this, will come in obviously in a minute. So they made projections at Newlyn and Portpatrick. For people that don't know where Newlyn and Portpatrick is, Portpatrick is up here on the northwest coast of Scotland and Newlyn is down here. So the Portpatrick site is heavily influenced and it's close to the centre of loading of the ice sheet, whereas Newlyn is much further away. And as we just said, it's not really that dependent on the British and Irish ice sheet. That will be more sensitive to other ice sheets, however you want to call them. So if you look at the prediction of future sea level projections at Newlyn, this sea level change from -0.2 to 1.2 to 2000 to 2100, as you can see, you've split it into the total signal, suggested the rise here will be over 1 meter. Great. You then look at the contribution from the ocean, Antarctic glaciers and land. GIA is all the way down here in this little tiny yellow line. So it's a really, really small contribution compared to, say, oceans and, I don't know, Greenland. So you might be thinking, well, why are you banging on that GIA is so important when the massive contribution to sea level around the Newlyn is to the ocean? So then you think, well, what's happening at Portpatrick? So you look at Portpatrick, And the future sea level rise there is less than 1 meter. So that's a lot less. And the reason it's a lot less is not because there's a different amount of ocean or a different amount of sea level rise from glaciers. It's due to the difference in the GIA signal. So the GIA signal at Port Patrick is minus 0.1, whereas at GIA at Newlyn was positive. So the reason why the paleo, or how good my GIA modeling was using the Holocene data and using all this paleo information, is because it influences the spatial variability at these sites. If the GIA signal was the same, the sea level projections at these two sites would be the same. So this is a kind of an example of using the paleo to tell us something about the future projections. So the question is, I made this new ice sheet reconstruction. We spent a really long time doing it. Does it actually make any difference for this spatial variation in the signal between Newlyn and Port Patrick? Because if we did all this work and it was exactly the same, you'd be like, well, then it doesn't really matter if your GIA model is really poor, it makes no difference. So this is a predicted GIA-driven vertical land motion. This is the UK. So minus 1.2, that's subsiding. So you're down here in Newlyn, you're subsiding in about 1.2 millimeters per year. That's no different, we knew that before. And then up in the center of the ice sheet, here's Port Patrick, you rise, and you're like, that's fine. So changing all the ice sheet reconstruction and making an ice sheet reconstruction that was actually correct hasn't really impacted on the magnitude of the vertical land motion. What it has done is change the spatial pattern. So this black line here, which you maybe hopefully can see, is where you shift from whether the land is uplifting or subsiding. So in the older reconstruction, which is this white line here, the area of uplift and subsidence was shifted to the northwest and it was much more circular. And now that we've changed the North Sea glaciation, the region of uplift is kind of expanded like a lozenge. So if you were trying to understand or project future sea level variation across the UK, this change in the GIA uplift is going to have implications, especially if you're looking at around the coast of Ireland and Northern Ireland, where you've changed from being subsiding to now an area of uplift. So it may be very minor changes that we've edited the sea level at 30,000 years, the ice sheet at 30,000 years ago, but it does ultimately have implications for GIA-driven vertical land motion. So then I thought, well, that was one example. Can I quickly go over a slightly different example? So 2018, Ben Horton and myself and the other people tried to use Holocene sea level data to understand marsh vulnerability to sea level rise and the rates of sea level rise. And this is what this paper was really looking into. How did tidal marsh systems respond to rates of sea level rise? So tidal marshes, as I'm sure, these little valuable ecosystems that sit around the coast and protect the coast from storms and they store loads of carbon. So maybe we know that they're really important. And they form this little narrow elevation range. So if there was a huge, really rapid rise in sea level, obviously the marsh would probably not be able to vertically accrete and respond in time, and then it would die and it would be lost, and that would really suck. So we were looking into using the Holocene relative sea level around the UK to see, well, what happened to these systems in the past when the relative sea level was changing? And can we use this to understand how the systems may respond to future rates of relative sea level rise? So yet again, I took a GIA model. This is the UK. All these little dots are sea level sites around the UK. And I made predictions of the rate of relative sea level rise at all these sites. It's not, rocket science. We've seen many a plot of relative sea level. Here's goes from 12,000 years to present, and you've got rates of over 16 millimeters per year to -8. So around the southern coast, 10,000 years ago, you've got rates of relative sea level of over 10 millimeters per year. By the time you get to about 7, you're down to 2 millimeters per year and 12 millimeters per year. So we took this information to say, well, this is what we knew the relative sea level was doing. What were the coastal systems doing? So not me, because I don't dig in dirt. Ben and Ian looked at all the information more in the cause and said, what's the sea level tendency in these points? Bear in mind, I'm not a data person. So this could tell you something about the change in depositational environment in these sea level cores around the OK, and say, what has been the change in the marine influence? So if you've got a site, I don't know, for instance, in Wales, and it's got a positive tendency, then it's had an increase in marine influence, and then this system's retreated. So you'll say, well, when this system was retreating and there was a loss of the tidal marsh, what was the rate of sea level rise? And vice versa, sites that had a negative tendency, so a reduction in marine influence, they were likely to have advanced. What was the relative sea level doing then? And then, this is a lot of words. So we split it into this negative tendency and positive tendency. So you can think, if I'm blue and I'm on up here at 10 millimeters to 0 millimeters per year, it's likely my tidal marsh has retreated. Where obviously if the relative sea level is down at -5 millimeters to 0 millimeters per year, it's likely my tidal marsh has advanced. They've all just been normalized. So that's why the y-axis is a bit strange from 0 to 1, because you had some sites where, say, a -5, you might have only had 1 data point, whereas you could have had some sites at, say, 3, where you had 8 data points. So they've just all been normalized. So you can kind of get this relationship where you're like, okay, well, got an idea what the rate of sea level was and what happened to the tidal marsh. But this isn't necessarily very informative if you wanted to say, well, what's going to happen in 1800 or something. You want some more kind of statistics rather than sort of eyeballing a line on a graph. So Bob Kopp and Neen Carhill did some probability analysis and said, well, what is the probability of a positive tendency or a retreat to these given predicted rates of relative sea level rise? And they came up with this little graph that looks like this, from -5 to 10 millimeters per year. And they said, well, if your rate of relative sea level rise was 7.1 millimeters per year, got over a 90% likelihood your tidal marsh would retreat. So this is more of a kind of statistical relationship rather than eyeballing on a graph. So we're like, well, we know what's happened in the past. How can you use this to tell us something about what happens in the future? Because that's what we're more interested for. So they took this probability analysis and combined it with 2 sets of sea level predictions for RCP 8.5 and RCP 2.6 and said, what is the probability of a positive tendency or retreat in all these salt marshes or all these areas around the UK? And the headline was, mostly by about 2200, most of the salt marshes or these areas around here will have retreated. Whereas if you were, say, the 2.6 scenario, it would only be the areas around the southern margin because these are really subsiding. So this was just a final example of how we've took all this information about the geomorphology and what the ice sheet did across the North Sea, and we've used it to make predictions of the rates of relative sea level rise, and then we've used it to tell us how this information is relevant for the future case. So trying to link why the paleo is interesting for the future. That's the end.
Thanks very much, Sarah.
It's very strange speaking to yourself in a room.
Any questions in the room?
Hi, Sarah. Georgia speaking. So you focused on the southeast kind of Antarctic ice sheet graph, and on the southwest, when you had the bar plots comparing all of the ice models.
Yep.
And it seemed like on the southwest coastline there was a potential influence. So
yes, if you compare, so Georgia's questions was, if you compare the grey line and the blue margin, which are changes in Antarctica to the southwest data, there is very slight differences in the graphs. Very good eye spot. However, which I didn't mention, this small black bar here is the error bars on the data. So say, for instance, at 4,000 to 5,000 years ago, the difference between ice 5G, big Antarctica, blue, small Antarctica, is only about 0.5 meter. And the error on the data is 0.5 meter. So perhaps it would have been clearer if I'd said the differences have to be bigger than the uncertainties on the data.
All right, I just thought that the residuals on the southeast data are kind of, they don't really change at all through time.
No.
Whereas on the southwest data, they're small and then they increase. Does that mean that they've become more sensitive to changing Antarctic ice volume?
I mean, I don't think that the differences between the grey bar and the blue bar are larger than the error bars, but there is more variation on the southwest data than there is on the southeast data between the two differences. So there is slight more of a difference on the southwest and the southeast, and I think that's mostly due to the spatial pattern that goes around the coast. So the errors, the differences between the two models are larger on the southwest and the southeast, but they're still within the size of the error bars of the data, so not big enough to be kind of relevant.
Yeah, okay. Thank you.
Way. But no, good spot on those tiny error bars. Eagle-eyed.
Okay. Well, thank you again, Sarah. Oh, sorry, there is a question.
Oh.
I missed you.
Thank you. I'm speaking out of the distant geological past because I was a postgraduate student at Imperial College in the 1950s. That gives you an idea of how distant I am. Now, at the time that I was studying, we made a great play about the value of raised beaches.
Yep.
Now, I haven't heard a single mention of things that are available in the field for people to look at and to use to establish criteria such as you're putting forward. Are these features like the 25, 50, and 100-foot raised beaches no longer of any value? Is the distribution of glacial erratics of no value? There was never any mention of the influence of the North American ice sheet in the British Isles at that time, to my recollection. I may be wrong about that, but I have no recollection of it. But just looking at it from my viewpoint, I can't see how you can postulate sea level changes without taking into account the value of features in the field, which I've not heard a single mention of so far in the 2 days of the conference. Your conclusions have been based so much on modeling rather than on field evidence. I want to know, are you taking field evidence into account in your postulations for changes in sea level?
So I'll mention erratics last, but yes, I have not any point in this presentation showed shorelines. So my modeling results is all based on data. So the Brit Ice Chrono project was a data constrained ice sheet. So that's all based on geomorphology and dating. So that input part of my ice sheet is all based on data. I have not used the raised beaches or shorelines if they haven't had a date, because I was unpaid when I did this work and there's only a certain number of Sundays. However, the next stage to do this work would be to say, okay, the shoreline data, such as you've said, these could be all informative information such as limiting data. So they are a second data set that could definitely be used after this to follow on the study. But we wanted to use information that had some sort of dates for this point. On erratics, I don't use erratics in this study. The PALGLAT project led out of Sheffield is modelling erratics and erratic movement across the UK, because there's a database of all erratics that have come out the Shap granite and where they've moved around the UK. So that is being done, but it's not been done as part of this project. So I have shown a lot of modelling, but all the stuff from the Brit Ice Chrono that went in to make my ice sheet reconstruction That was all data. Stuff that people have gone out, dug holes, looked at, mapped. But yeah, so erratics are a very useful thing. Coming soon, I suppose I would say.
There's also 5,000 sea level data points in the database that Sarah uses, which includes great shoreline, estuarine deposits and things. So they are all in that database that Sarah then
Thanks for that question. So any more questions? No? Okay, if not, thank you, Sarah. We're going to now move on to so we've got the virtual poster session today, which is on the Padlet, and we'll put the QR code back on the screen at the end. But we've also got some introductions to those virtual posters. So some of these are going to be videos that have been pre-recorded. Others are going to be, there's a couple of in-person ones, and then also some people who might be online. I'll ask you also to give a quick introduction to your talk. But we're going to start with Jamie O'Neill, who's pre-recorded a...
Hi, I'm Jamie O'Neill. I'm a postdoctoral researcher at the University of Exeter. My poster title is Modelling the Antarctic Ice Sheet Under Warm Pliocene Climates. Presents work that I did as part of my PhD at King's College London, which was looking at Antarctica in the last period when atmospheric CO2 concentrations were as high as they are today, the warm Pliocene. As I'm sure many of you know, sea level in the Pliocene was potentially tens of meters above modern, suggesting mass loss from the ice sheets, including Antarctica. Simulating significant Antarctic retreat in the Pliocene has proved difficult in previous studies, however, and specifically capturing retreat into East Antarctic subglacial basins has been a challenge. To capture this retreat, some models have included new processes and parameterizations, such as the marine ice cup instability. We wanted to explore uncertainty of the Antarctic Pliocene sea level contribution and see whether we could capture the range in Antarctic mass loss and use the period to constrain our model ensembles. To do this, we used the bicycles ice sheet model with a 4 kilometer finest resolution in a framework that didn't include the marine ice cup instability. We ran a series of perturbed parameter experiments and compared our ensembles to paleo data. We simulated a really wide range of Pliocene sea level contributions, with our results showing particular strong sensitivity to the basal sliding parameter. We also showed that combining paleo data constraints effectively reduced uncertainty in our ensemble. So thanks, and if you want to have a look, please see my poster and feel free to email me any questions that you might have. Thanks.
Okay, thank you, Jamie. Next, we've got Jim Marshlick, who has actually got an in-person poster, it's also online. A quick intro.
So, hi, yeah, I think Tina introduced my other poster yesterday, which is looking at some early Miocene sediment provenance record from the Ross Sea. I suppose this is kind of related to that, so it's all about trying to basically try and make those sort of predictions a bit more quantitative and sort of convert these sediment provenance records with some sort of ideas of where the erosion sped up in the past into more sort of numbers of what that means for sea level. So to do that, sort of use an ice sheet model output to make some predictions of where erosion rates, and then using that to also the ice sheet model to route sediments to the ice sheet margin, and then made some estimates of things like iceberg grafting, bottom current movement, and gravity flows to sort of use that to make a sort of prediction of provenance indicators, in this case, neodymium isotopes, sort of map around Antarctica. And then the sort of bottom panel there is applying this to some Pliocene ice sheet model simulations and comparing that to an IDP site from offshore of the Wilkes Glacial Basin. And it turned out that we could quite nicely use this to sort of place an upper bounds or help place an upper bounds on the amount of ice sheet retreat in this area. and use that to sort of make estimates of Pliocene ice. So yeah.
So next we've got another pre-recorded video by Malcolm.
In southwest England and in Brittany and the Channel Islands, we have a very good record of sea level changes that can be documented through the Pleistocene and Holocene. Some of this evidence comes from raised beaches, submerged forests, submarine sea cliffs, but in particular cave systems where we have megafauna preserved. Some of the caves are below sea level at the present time, although they were above sea level during glacial periods. Within these caves, we have probably 3 isotope stages recognized going back to MIS 7. The foraminifera that have been washed in can be used to look at the environments that were providing the sediment. Within Plymouth Sound, we have the drowned River Tamar, and we can see the record of microfossils within the salt marsh, estuarine muds, and marine sands that make up that borehole record. In the Channel Islands, between Jersey and France, we have a record of boreholes across the exposed area between the two countries. And here we've got the additional bonus as the peat layer, which can be radiocarbon dated, can be attached to the stable isotope record and the micropaleontological data. This gives us a pretty accurate record of the last 9,000 years of Holocene record. So in this area of southwest England, we have a good record of the main isotope stages back to MIS 7, mixing together the physical features, the microfossils, and the megafauna.
Okay, thanks, Malcolm. We're next going to switch to Mathieu, who is going to join us online to introduce his talk. Sorry, his post.
Hello, can you hear me?
Yep, we can hear you.
Okay, I share one moment my screen. Okay, so can you see my screen?
Yes, we can.
Okay, that's great. So thank you so much. Actually, my presentation is focused on relative sea level assessment along the western coast of Africa. This area was a sort of black hole for the sea level reconstruction because we have lots of data of the Atlantic coast of Europe. We have lots of data of the American coast of Europe, but we didn't have data standardized, at least, for the Holocene along the western coast of Africa. That is an important far-field site for relative sea level reconstruction and tuning of the GIA models. So actually, the few data available were from the southernmost tip of the continent, so between Namibia and South Africa. It's a paper by Andy Cooper et al. In 2018. So I put together sea level database that was very, very complex, honestly, probably the most complex database I have ever done, because there is a lot of great literature, lots of, the large part of the literature is in French, it's not in English, and it's not easy to access. But finally, I put together 230 sea level index points and about 100 limiting points. I discarded several data because they were not very good. And the type of data are essentially salt marsh, mangrove peats from the intertropical area. But we have also lots of other sea level indicators like raised beach or other geomorphic data, and also some very beautiful vermeted reefs, so fixed biological indicators. As you can see, the sea level reconstruction is quite long. So we have data for the last 30,000 years with lots of marine limiting dates from the Guinea Gulf, cores in the Guinea Gulf. And then we have a nice suite of sea level index point for the last 15 years. As you can see, the sea level rose quite rapidly up to 8 to 9 kilo years ago. And then we have the establishment of relative sea level ice stand that it is quite interesting, shows lots of differences between the region of Western Africa. So the most classical ice stand is recorded in Morocco and in the northern part of West Sahara, where we have sea level ice stand that is essentially between 5.7 and 4.5 kilo years BP. Then we have a very small ice stand in Senegal and Mauritania. And in the Gulf of Guinea, we found very weird sea level evolution, because we have actually a couple of ice stand. I know that this is very complex to explain, but actually we have a first ice stand that is the classical one of the mid-Holocene, but then in several sites from practically Ghana down to the Cameroon, we have a second ice stand that is in the late Holocene, that is a bit younger than 2000 years ago, that is presently very complex to explain with the GIA models we have. And it's also difficult to explain with vertical movements, local vertical movements, because we found it for several hundreds of kilometers. And also the area is a passive margin that is very tectonically stable. The other point is that southwards in Congo, Angola, we have again a couple of ice stand, and especially in Angola, we have a very high relative sea level during the transition between the mid and the late Holocene. So now we have done lots of stats in order to understand and constrain better all of these different relative sea level evolution, and probably that there is an isostatic origin of this an isostatic control, essentially siphoning and continental leveling that control the variability of this ice stand pattern along the western coast of Africa. Of course, this is not only related with the northern hemisphere ice sheet, but is probably related with the contribution of the Antarctic ice sheet. Many thanks.
Thanks, Matthew.
The next poster is by Yossi. Not sure, they're not online. You in the room? Not, we will move on to the next one. So final virtual poster is by Gwilym, who is here to introduce his poster.
What's the name again, you said?
Gwilym.
Yeah, yes. Yeah, sorry. Okay, hi everybody. My name is Guillaume Jouve. I'm working for Exhale, formerly Blue company, southeast of France, in the sonar system division. So I'm presenting to you a poster about a scientific collaboration we have with several southeast of France universities and Andromède Oceanology Association, trying to understand what was discovered 10 years ago that are coralligenous rings that are laying at about 115 meters on the seabed off of Cape Corsica, of an unknown origin and no analog past or present that have been discovered. So it's quite new, and we are using several sedimentological, geochemical, geophysical approach. So I'm presenting to you the project, starting like 1 year ago, and with also scuba diving and hyper-saturated scuba diving conditions and projects. So yes, so come to my poster and I will explain to you what we are doing with our systems. Thank you.
Okay, thank you very much. So lots of really exciting posters. As I said, they're all online, so please engage with them. We've got 40 minutes. We're not going to give you lunch until 40 minutes time, so please just go on the Padlet, look at all the posters, and please comment on the ones that are interesting to you. Okay, thank you very much.
So, I mean, so far I've been listening to very amazing talks, and I was saying to many people here that I found that the progress in the community has been very impressive, both in reducing the uncertainties in sea level rise and high stands in the past periods, and also both in terms of modeling a bit. So I think it's very important that the communities keep advancing right now. So it's very impressive. Also because I've been focusing mostly on SCAR community and activities last year, so I've missed a lot of different things. And once wake up, just realizes that the community has been flying away. So that's great. I mean, actually. I wanted to provide a bit an overview of why perhaps it's important to consider the long-term changes of Antarctica for the sea level projections. This is something that I've been talking a bit about at the COP27, because we are trying to push the long-term projections, sea level projection, long-term, like multi-centennial projections. So, well, for the Antarctic ice sheets, it's not very complicated to understand the impact. So, many sectors of the Antarctic ice sheets are marine-based, okay, right now. So it makes the Antarctic ice sheets, highly vulnerable to both atmospheric warming and oceanic warming, actually. And well, when we talk about oceanic warming, we all know now that it triggers some instabilities, okay? Both because ice shelves are thinning and because the buttressing effect is removed when ice shelf disintegrates, which makes the grounding line to retreat back, okay? But also it has been proposed another mechanism that is the marine ice cliff instability that basically originates more from surface melts, okay, that penetrates the crevasse and provokes some hydrofracturing and runaway processes and the grounding line slipping back anyway. So how much time does those marine ice sheet instability takes? I mean, usually, in ice sheet simulation, it takes a couple of centuries or 2 to 3, 4 centuries. But the importance of that is that it has a fast trigger. That's why we are all focusing on tipping point right now. We are not sure that oceanic temperature have crossed the tipping points. And the tipping points might be also different amongst the different regions of Antarctica, okay? And then it has long-term consequences because the marine ice sheet instability or the marine ice cliff instability are runaway processes until the grounding line reaches a new dynamical equilibrium that might be reaching a pinning point in the bathymetry, or just the ice flow that is not accelerated enough, stop accelerating, so stop the discharge. And Rob has been simulating that in his simulations in his paper 2016. Well, I mean, actually, I just wanted to show you a bit how long it took in his simulation. So it just simulated the disintegration of most of the West Antarctic ice sheets by 2300s. So it's a couple of centuries, let's say. So I wanted to provide a paleo perspective of those marine ice sheet instability, because it has not always been the case. And I think Rob, at the end of the afternoon, will be extensively talking about that. So I will just be talking kind of very superficially about that. So what are the ingredients of marine ice sheet instability? The first one is a subglacial bed that is below sea level, okay? Otherwise, we don't have any marine base sectors. Possibly a bed sloping toward the interiors, but that's not let's say, a necessary conditions. You can trigger marine ice sheet instability even if the bed is not sloping toward the interior. And a grounding ice sheet plus ice shelves. So, okay, it means that you need to have some ice shelf forming at the front of the ice sheet. So you need to have ocean conditions that are cold enough to allow ice sheet expansion, ice shelf expansion. And you need to have warm water intrusions, okay, below the ice shelf, okay? Those are the conditions, otherwise you cannot trigger any instabilities. So what about the first ingredient? So a subglacial bed below sea level. So we know that during the ice sheet expansion, okay, the ice erodes the bed and transport the sediment up to the margins where it can accumulate, okay, at the foot of the continental margins. And it also accumulates sediments while retreating back and forming some frontal moraine. So we have some cases where you have nice frontal moraines, the successions that have been preserved on the continental shelf in some of the areas, in the Ross Sea, in other bays, probably also in the Weddell Sea, if one day we will be able to penetrate there. And so by making bathymetric reconstruction and evolution through time, you can understand, I mean, those ones have been done by a guy. I mean, so sorry, the format is bigger, so we don't see citation here, but so those reconstructions are from Guy Paxman. And of course, I mean, you can see that the main marine base sector of Antarctica has been evolving through time quite a lot, okay? Just arriving to this situation. So the expansion of the marine base sector has been increasing, okay, during the time. So you can imagine that the feedback with ocean has also been evolving through time. What about a bed sloping toward the interior? So this is interesting to have a look at the continental margin evolution, because this tells you a lot about the Antarctic ice sheet dynamics evolutions, okay? And then you can integrate with the rest of the proxies to understand the relationship with climate evolution as well. But if you have a look at the transection here, it's a transection in the Ross Sea. I always use this one because I find it very dynamical, but I can assure you, you can see the same thing in other sectors of Antarctica. And you make a line drawing. I didn't do it myself. My colleague did it. Plenty of patience. You can see the evolution. Each color represents a time slice, okay, spanning from the Oligocene to the Pleistocene, with some Pliocene being in the red, the intermediate red package, for example. And you can see that the slope of the continental margins has been evolving from seaward, okay, with the ocean there on your right, to slightly inward, okay? So this is something that has been built up because of addition of glacial isostasy, because the ice sheet has been becoming bigger and bigger, so the isostatic depression has been also bigger and bigger. So it also influences the deposition of the sediments on the continental margin, okay? So what we have today is really the results of the combination of the feedbacks between the climate that allows Antarctic ice sheets to grow bigger, and also the solidars that allow also for depression and influence the geometry of deposition. But anyway, so through time, we have an evolution of the expansion of the marine base sector and an evolution of the slope of the continental margin itself. So then when you put that in an ice sheet model and you try to understand the sensitivity of an ice sheet to oceanic condition while putting this evolution of the subglacial bed in the simulation, you can see the color shows you the increasing sensitivity with the increasing expansion of the marine base sector and also the over deepening margin toward the interior, okay? And the last one is the present day bathymetry. The first one is the Eocene bathymetry, so mostly terrestrial and mostly marine based, okay, for West Antarctica and some of the sector of East Antarctica. So you definitely increase the sensitivity to oceanic forcing, okay? You also, I mean, those are simulations from Ed, and I think this was to show that the volume of ice that you can accumulate on a different subglacial topography with a largely increasing marine base sectors is smaller and smaller, okay? So at the beginning, it's easier to accumulate ice on a fairly exposed bedrock, okay? Because it's only sensitive to atmospheric warmth. And little by little, it becomes also sensitive to oceanic warmth, but the climate in time, we know it has been also cooling. So you have perhaps larger ice sheets, but when they retreat larger also because most of the sector that are marine based are also more sensitive to this instability process, okay? And then the fourth ingredient was warm waters intrusion below the ice. So in the Miocene, let's say until the Pliocene, so we say the margin, okay, is a slope that is seaward. It's also less expanded northward, okay. So the relationship with the intrusion of CDW, the circumpolar deep water, which is the, let's say, water masses providing the heat transport toward the grounding lines, has changed as well. I mean, you cannot compare heat transport nowadays and heat transport in the Miocene with a completely different morphology of the continental margin, okay? So during the Miocene, it was warmer, much warmer, okay? So you had a lot of circumpolar deep water that intruded also on the continental shelf. And because the climate was warmer, all the synoptic atmospheric system was also shifted southward, means that the westerlies were also southward, so it pushed further the circumpolar deep water toward the Antarctic margins. So we had very warm oceans, and we had an ice sheet that was relatively sensitive to the warmth, because at that moment, the marine base sector of the Antarctic ice sheet was only developing. They were not prominent as they are right now. So the sensitivity to oceanic warmth was there, but not too pronounced, let's say. And then we arrived to the Pleistocene, where our continental margin has the configuration that we know now. So it's a bit higher, it's more expanded, okay? So it makes it more difficult for the circumpolar deep water to intrude toward the grounding line. And because our climate is also a bit colder, okay, compared to the Miocene, all the synoptic atmospheric system is shifted a bit northward, okay? So it means that if you want to enhance the intrusion of circumpolar deep water, you need to have strong southward shift of the westerly system, for example, okay? So it means that it happens only in times of exceptional warmth, okay, when all the atmospheric cells are pushed up southward. So it means that that's why perhaps we have only testify of ice sheet retreats during peak greatest interglacials during the Pleistocene. And because of the expansion of the marine base sectors, we have polar oceans that are only slightly warmer than today during the Pleistocene interglacial, but only slightly warmer. But on the contrary, the ice sheet is very sensitive to this little warmth that is brought to the grounding line, because now most of the marine base sector are very deep, okay, and we have large areas of ice shelf. And then we also have to consider the Antarctic in the broad system, okay? It's not only what's going on at the grounding line of the Antarctic ice sheet, but it's also about the heat transport through the hemispheres, okay? And in paleoclimate, we have this process that is called the bipolar seesaw. Bipolar seesaw is a mechanism that transfers the heat from the northern hemisphere to the southern hemisphere, okay? During the melting of the Greenland ice sheets, okay, that just release some fresh water, okay, in close to the convection site of the North Atlantic deep water. And then as such, it just weakens the heat transport toward the hemisphere and has some consequences also on the atmospheric system, okay? So because of that, okay, the heat is transferred to the southern hemisphere and then enhances the heat transport toward the Antarctic ice sheets, and as a consequence of everything, just triggers some disintegrations of the ice shelf there. So it's not only of, let's say, spontaneous intrusion of circumpolar deep water, but at the bigger scale, these are the feedback loops that might also influence the Antarctic stability. So do we have any evidence of such instability? I think, yes, I mean, and because we have been dating this frontal moraine on the continental shelf, we know that it's about 200 to 600 years for the instabilities, depending on the morphology of the fjords of the continental margin, of course. And those are the papers that we have with some, let's say, grounded evidence. But I know there are other ongoing works that are showing some results in this direction. So we do have like evidence of, let's say, past retreat of the grounding line. When did this happen? So this is a broad picture of CO2 evolution in time since the Antarctic glacial inception. And we know that the ice sheet has been shrinking during the mid-Miocene climatic optimum. We have some few evidence from the seismic profile of the continental margin. We knew that during the Pliocene, many sectors have been shrinking. We don't know if collapsing, but at least shrinking very much. With CO2 that was around 400 ppm. And then we know that some ice sheets, some grounding line has been retreating in some of the sectors as well during the Pleistocene, while the CO2 was around 300 ppm, okay? So it means that CO2 sometimes can be the trigger because of the, let's say, surrounding increase in temperature. Sometimes it might not be the case because during the Pleistocene, the CO2 is very low, okay? But we still have sign of retreat. So it means that we have other mechanisms like ocean ice sheet feedbacks that are a little bit more independent than the global CO2. And then, of course, we have projected our ice sheet shrinking in the future, but with a CO2 that can be higher than 450 ppm in the atmosphere. And now, if we have a look at the projections, okay, here I've shown you the lower emission scenario that is closest to Paris Agreement, and the high-end scenarios, okay, that is plus 4.4 degrees by the end of century, and the contribution of the Antarctic ice sheet is quite small in this scenario. But the real impacts are on the long terms, okay, so it means multi-centennial timescale. And if we do that, okay, by 250, even for the low emission scenarios, I mean, global mean sea level is above 1 meter, and the contribution to Antarctic ice sheet doubles, okay? If we look at the IN member scenario, of course, Antarctic contribution represents most of it, okay? But now if we account for, I mean, those scenarios do not account for this marine ice cliff instability I mentioned at the beginning, but if we account for it, okay, we push both scenarios. So even for the low emission scenario, we arrive to a multi-meter sea level rise with Antarctic ice sheet contributing to more than half of that. And very, very large numbers in the case of the high-end member scenarios. But so the main thing is that the sea level commitment depends on how much and how fast then we mitigate the carbon emissions. And most of it is due to the thermal inertia of ice sheet and oceans, because of course an ice sheet absorbs the heat as the ocean does. And it takes a long time to absorb, but it also takes a lot of time to release. So even if the climate cools in the future, the ice sheet still has some heat that has been accumulating and will release it by retreating, while the climate context will be perhaps cooler than now. And that's why, I mean, sea level rise will continue. And then we have the runaway effect of the ice sheet instability. So if some sectors cross the tipping point, it will anyway have multi-centennial consequences anyway. So now if we put the sea level projection in the perspective of what we know about paleoclimate sea level change. So during the mid-Miocene, I mean, the uncertainty is very huge, but we are around 20 meters or more of sea level rise compared to today. And during the mid-Pliocene, we are around 15 meters or even lower, as I've seen now updated numbers. During, for example, one of the super interglacial, we are around 15 meters, but there are not a lot of constraint on that. Then around 5 meters for the last interglacial. And if we put the high-end member scenarios, this is what we get. So definitely, can we say this is science fiction? I'm not so sure about that. I think it's very realistic, okay? And that's why we should be a bit afraid of that, in the sense that, well, those numbers, even though they're projecting the future, they are kind of realistic in perspective. So sea level rise is unavoidable. This is on the basis of all the data we have from paleo to today. So it will involve multi-generational adaptation action, but it will reach the limits of adaptation if we continue our emission without mitigating anything. So the impact of sea level rise, it's not only about global mean sea level rise, but it's also about regional impacts. So to be added with high tides and risk and damages and coastal erosion and saltwater intrusion, etc. And some papers show that with half meter of sea level rise, I mean, 2 billion inhabitants will be impacted by the end of the 21st century. So that's a lot. And we are already impacted a lot. I think there are many countries that are very low-lying, that are already starting to migrate little by little. So we will have a big international conference in Trieste this September with this CAR group that is focusing on instability and thresholds in Antarctica to discuss all those aspects from the paleo to the future projections and discussion with some practitioners. Thank you.
Hey, Flo. So do you think then that, like, with that developing sensitivity to ocean and marine ice sheet instability, that even like our future models aren't going to really be, I guess, encompassing that if it's worse than it was in the recent past, and that's all we're basing it on? Like, do you think that with time that effect's going to get worse, basically, and do our models include that worsening effect?
Yeah, well, so I would say Rob's model is pretty pessimistic. So I would say that's the pessimistic side of the projections, and ISMIP 6 models are the optimistic ones. So I think we have the whole range of pessimistic to optimistic, but in the sense that well, right, in the case of climate models, perhaps we still lack of sensitivity. I think we all know that. So present day models are lacking of sensitivity to polar amplifications. Is badly reproduced. So I think it's a demonstration that we are lacking some representation of processes in the climate models. And I think there is substantial improvement to do in the oceanic circulation models, because they are the less flexible models right now. There are a lot of approximations also in the oceanic models, and the way the codes have been developed makes them very complicated to couple to the other components and to run long time scale simulations. So there are improvements to be done by every bit of the community. It's not only ice sheet modeling. For the ice sheet modeling, I think we are exploring the range of all the possibility of physics. But however, in the case of instabilities, we only have paleo data now to calibrate the physics, because we don't have real observation of marine ice sheet instability. So we cannot even pretend some sectors now are subject to marine ice sheet instability. We don't have enough long data time series long enough to do that. So it's only speculation. So paleo data now are essential for ice sheet modeling community, probably also for the climate community, to push more to understand why there is this lack of sensibility of the Earth system in general. So yeah, there is a good probability that we are not able to capture the worst case in general, and I would say more the rates of climate change and ice sheet melting probably.
Thanks, Flo, for a great talk. So I'm just following up on the question in the same direction, because I know you think a lot about the ocean as well, and it comes from actually having marked an undergrad thesis last week, which looked at CMIC 6 model outputs for temperature and salinity in the Ross Sea and Weddell Sea, just kind of analyzing the UTRA samples and kind of looking at it. And one thing which struck me is they came up with temperatures of 4 degrees warming for SSP 8.5, which is of course even lower than the global average, right? So question to you, is that the general observations that some of the CMIC models don't see the polar amplification we probably would all expect? Because I was surprised by seeing that. And then what can we do to integrate better that kind of climate ocean knowledge with kind of the ice sheet community? Because as we're trying to understand our sources, obviously we need to integrate the whole system, like you rightly pointed out.
Well, so what is very complicated for a climate model is to really reproduce the right location of the main synoptic feature of that might be atmospheric or oceanic. And models strongly disagree, for example, on the westerlies location and on the westerly behavior. And some models propose some 2 branches that are more close to the observation, and some model proposes just 1 branches that just migrate a bit north-south, like we have the representation of our northern hemisphere jet stream right now. So if you got something wrong at synoptic level, then the heat transport is biased. And so the consequence is that if you if you take a climate model that is coupled atmosphere, ocean, and you don't have the right location of synoptic fixture in the atmosphere, then it becomes very complicated to have the right location of the gyres. And then you have a wrong temperature estimate. And the second thing is the resolution of the grid of the climate models, of course. If you take very coarse resolution, like 1 degree or 2 degrees, it impacts a lot on the convection side in the ocean models as well. And so sometimes the convection does not happen where it should happen. So it also biases a lot the representation of vertical temperature, but also, let's say, surface temperature and subsurface temperature, and then the heat transport as well. So there are different aspects in the coupled climate system that that leads to those kind of biases. Now, not sure how to really solve the problem. I mean, so we know that in the Southern Ocean we are lacking of observation anyway. So we need to have a better representation on the water masses evolution right now, because we are not so sure sometimes where they are. And Weddell Sea is typically an area where we lack of observation. So it's very complicated then to tune the models to reproduce something that we don't know. And in the Ross Sea, Ross Sea is more spotted, but it's also punctual. So what we need is what the Southern Observing Ocean System is doing, is trying to coordinate some network of moorings or a continuous observation system, because we need the continuity, because now we know, for example, in the Ross Sea, the Antarctic bottom water representation, formation has been changing a lot over 2 or 3 decades only. So if we only have punctual observation, you might not catch this evolution. That could be also of importance if we want to understand where are the tipping points also for the ice sheet. So there are different aspects from the observing system to the, let's say, the more intrinsic physics of the climate models.
Yes, I was wondering if you had considered the role of sea ice in your future modeling. Because I think recent publications suggest that as you melt the ice shelves from underneath, what you're doing is you're supplying fresh water into the Southern Ocean, which could actually expand the area of sea ice, which might well slow the processes affecting the Antarctic ice sheet. And I just wondered if you'd had time to fit that into your modeling.
Okay, so the answer is yes, not personally, but the colleagues in the community have done so, because in an ocean model, most of them now, sea ice is interactively forming during the simulation. So what happens is that, yeah, this sea ice feedback is important. However, that's only what happened at the surface. So at the surface, you increase the albedo, so you locally cool the temperature, okay? But however, as we say, okay, I didn't mention that, but in Antarctica, there is almost no melting, and perhaps melt at the surface will happen at the end of the 21st century, only in the worst case scenario, let's say SSP 8.5. The main feedback is perhaps getting things even worse, because then when you make sea ice cover at the surface, you trap most of the heat below, then you enhances the heat advection toward the grounding line. And so you might even enhance the marine ice sheet instability, or trigger some marine ice sheet instability in sectors where perhaps it was not occurring. So depending on the time scale considered, at the moment, momentaneously, the sea ice albedo increase might compensate a little bit for the melting at the surface. But on a longer time scale, probably marine ice sheet instability wins on this kind of feedback.
Can I ask a supplementary?
Very quick one.
Yeah, very quick. Okay. You talked about 500 parts per million carbon dioxide for your 2300 scenario. But if you were thinking in terms of CO2 equivalent, it's already 500.
Yeah, it's already 500. Yeah, no, sorry, I just say more than 500, but actually in the SSP 8.5, it's 1,000 ppm by the end of the 21st century. So we don't know how it will be in 2300. Would be the honest question. We have not done yet scenarios to really project them. It's ongoing, but yeah, you're right.
Thank you very much, Marcus.
It's really lovely to be with you all. When I tend to think of historic sea level, I tend to think of sea level over the last 100 years. To me, that's quite far back. So it's really nice to be with this community and expand my thinking. And thanks to Tasha for very patiently explaining to me paleo sea level over many years. When I saw that this conference was happening, I've been doing a lot of work in London. I thought it'd be really good to come along and share with you. There's 139 cities around the world with populations of, upwards of 10 million on the coast that are at risk of sea level rise. So the one that we're all in is London. And this panel on the bottom shows you you can see the main river channel there, but in blue, you can see all of the areas that potentially are at risk of flooding. And it's actually quite staggering when you look at the statistics here. So within that zone, you can see it at the top. You can see the Thames Barrier, which I'll come on and talk about in a minute. But across the whole of that region, not just in central London, but the whole of the Thames, there is 320 billion pounds of residential properties, 1.42 million people, 56,000 commercial properties, 2,400 kilometers of roads, 116 tube stations, you've probably caught some of those today, 500 schools or education, more than 700 hospitals, clinics, health centers, 4 World Heritage sites, and so on, and so on. And it's been estimated that, London contributes about 250 billion to the UK economy, and a lot of that would not exist unless there was flood defenses in place. For the online people, this is what you missed. This slide and this slide. Hopefully you heard me speak there. Summary, lots and lots of stuff at risk of flooding in London today without any sea level rise at all. Now, the North Sea has a very, very long history of flooding. There's an event that occurred 1,000 years ago that killed 100,000 people. But if we zoom back into more recent history, by far the most significant event was 1953. We've just had the 70th anniversary of that. More than 300 people were killed in sort of southern England. We had a very significant event in December 2013. Thankfully, no one died, but it was similar water levels to 1953. It shows you how far we've come in terms of storm warnings and flood protection. Now, these events have led to a steady growth in flood defences in London. And I really love this figure from Greenwich that just shows over time. So there was a very big set of floods in 1877. And you can see the first raising of flood defence levels there. We had another big event where the last time central London was flooded was 1924. 10 people were killed. Flood defences were raised. You can see a series of subsequent defences to where we are today. So although we have this lots and lots of flood risk in London, overall it is reasonably well managed. We have over 330 kilometres of seawalls. We have the Thames Barrier, which I'll talk about in a minute, but we also have these 7 other smaller barriers, all working together in unison. Not only that, but we have 500 little bits of infrastructure, little gates. All of those gates, all of those seawalls, these big storm surge barriers all act to protect London. The Thames Barrier is the jewel in the crown. How many of you, just put up your hands if you've seen the Thames Barrier in person? I'd highly recommend you go there. It's really worth a visit. So the Thames Barrier was called into place after 1953, but it took 30 years to get the political approval and then to actually build it. Construction started in 1974. It was completed in 1982. It cost about 1.6 billion pounds, and it was first used to protect London about 40 years ago on the 1st of February 1983. It was opened by the Queen in 1984, and it's been used about 207 times. So London has been protected from flooding on about 207 occasions in the last 40 years. So we have a reasonably good protection integrated system of defences in London. But actually, 10 years ago, it was recognised that the tidal flood risk in the estuary was changing. obviously partly to do with climate change, sea level rise while we're all here. But it's not only that, there's far more people, infrastructure and property in the floodplain than there was 20, 30, 40 years ago, or almost double. And not only that, but these defences are now actually quite old. Some of them are well over 100 years old. The Thames Barrier is already 40 years old. So the Environment Agency recognised that it was time to really think about the future of the Thames. And they recognised that without doing anything, sorry, this is a bit of a rough figure, but these are the areas, sort of green is relatively safe, orange is where we're starting to have issues, red is where we have big issues, but without doing anything, without any upgrades, at different time slots, these would be the areas that are significant risk. And you can see, particularly with sea level rise, large parts of the estuary would really come under pressure. The existing systems would come under pressure unless there was significant upgrades to the system. So a team of mainly the Environment Agency, but working with lots of stakeholders, came together to create what's called the Thames Estuary 2100. And hopefully most of you have seen it and heard about it. And it's one of the most, if not the most innovative flood management plan that's really ever existed. It's starting to be copied all around the world. And this has 5 main goals. So to manage the risk of flooding to people and property in the estuary, but not only that, it's got a goal of about sustainability, resilience, protecting the social, cultural, commercial value of the Thames, obviously adapting to the challenges of climate change, but also trying to enhance and restore the sort of natural ecosystems. So just very, very quickly, the plan has 3 main time frames. So we're currently in the first timescale that runs until 2030. And this is not so much about updating, but just about maintaining and improving the existing flood defenses that are already there. The middle phase that starts in 2035 to 2050 is then about raising the defenses, improving, upgrading some of these smaller storm surge barriers. And then we have a future option which takes us from 2050. And this really is about the future of the Thames Barrier and raising flood defenses. We also have what's called the Thames Estuary Management Plan, which is the team that's actually pulling that into place. Now, the plan is really, really innovative in that it's an adaptive plan. Before this plan, flood management tended to be quite static. But it's not many people realize this, but it's adaptive in 2 main ways. First of all, they have a series of options in which they can protect the Thames. So if sea level rise is less than 1 meter, so up the top, you've got your rate of sea level rise, but if sea level rise is less than 1 meter, actually there's a pathway where we can raise existing defenses, we can introduce some flood storage, and we can protect the estuary. But if sea level is more than 1 meter, then we have to start to think about new Thames barriers, right the way through to actually we can probably protect London to up to 4 to 5 meters of sea level rise if we put in a barrage. That would fundamentally change the estuary. The estuary would become freshwater. We'd build a dam, we'd have to pump water out. But they've identified these series of sort of 5 main pathways that we can take. And depending on how fast sea level rise is, we can shift between these different pathways. And currently, this is the sort of main plan that we're following. So it's adaptive in that sense. But it's also adaptive in a second sense in terms of the timings of the key interventions. So here we have the year 2000 through to 2100. And at the moment, they're following this sea level trajectory here, which is the 95th percentile of the UKCP RCP 8.5, I think it is, scenario. And they've identified a series of interventions. So the first intervention is 2040, where we raise defenses downstream of the barrier. Now, currently, the plan is to do that in 2040, but if sea levels rise faster than projected, we can move that 10 years earlier, for example. We need to raise defenses upstream of the barrier in about 2065, but again, we can move that earlier. And at the moment, a new barrier is planned for 2070, but again, we can move that earlier. We'd have to raise defenses again in 2100. So you can see the plan is adaptive in these 2 main ways. However, sea level rise is not smooth. You know, on a year-to-year basis, there's lots and lots of variability. And so actually, one of the things I've been talking to the Thames Estuary team about is, how do we tell with certain exactly where we are on this? Are we following this trajectory? Are we higher? Are we lower? So that's the first issue. The other issue is we have quite long lead-in times. It took 30 years after 1953 that the barrier actually became operational. So if we need a new barrier in 2070, we need to start thinking about it now. We need to start buying land and preparing for that. Now, because the plan is adaptive, it needs to be reviewed quite regularly, and it's reviewed every 5 years. We have a smaller plan every 5 years, a bigger review every 10 years. So we're just we're just undertaking the 10-year review. But every 5 years, we monitor these 10 indicators of change. How fast is sea level rise rising? How fast is the extreme sea levels, which include the tide and storm surge component? How much is river flow changing? How good is the current flood defense system? Is that aging appropriately, worse than we thought? What is the operation of the Thames Barrier like? Development in the estuary, erosion, what's the state of the habitat, land use planning, public attitude to flood risk. So every 5 years, there's a review of each of those 10 indicators change. It's a very, very big review. It takes 2 or 3 years. The 5-year review was published in 2016, and we've just completed the first stage of the 10-year review, which you can log on and read about now. And so I've been involved in helping them lead through these 2 components of the plan. And that's what I want to briefly talk about in the next 5 minutes. Now, what's quite surprisingly is the tide gauge record is actually relatively poor in the Thames. We have one long tide gauge record at Southend, but very little data anywhere else. But we found out that the Port of London had quite good historic, handwritten, tabulated values of sea level at each of these 15 points, going back to 1911, when the Port of London Authority. Now, it's only time series of high and low water. And there was basically a whole room full of books going back to 1911, probably about 40 enormous books containing handwritten ledgers of high and low water. So we spent the last 2 years manually inputting that. There's a team of about 6 of us have inputted probably about 2 million values. We did it all by hand. So we created an Excel spreadsheet that mirrored the records, and we typed all of those in. We had lots and lots of issues in that some of the earlier data is in feet, some were 12-hour clocks, some were 25, lots and lots of different datums. So we had to very carefully look through each of the sites, look at what the datum was it ordnance datum, was it Trinity high water, and correct all of those. So here we have a time series of high water, time series of low water. Now, we had 6 sites across the estuary where we have almost continuous records going back to 1911 from these hourly. And so Sheerness, Southend, Tilbury, Silvertown, and Tower Pier spread throughout the Thames. So here we have 1910 through to 2020, and you can see those 6 records. They're quite noisy. Sea levels go up and down a lot, influenced by the river quite strongly. But if you just take a mean, that's the black. And actually, it mirrors the global change quite well, in that there was a very rapid rise in the 20s and 30s. Sea levels stabled a little bit in the 50s and 60s, but we've seen quite a rapid rate of rise since then. But what's really important is, where are we tracking? So what we can do is we can overlay that data with the UKCP projections. The latest projection was based on the slightly old DEFRA, which the plan was based on this pink value. This is a high-end sea level rise scenario one of our earlier speakers spoke about. So if you zoom in here, you can see, well, one, sea levels are quite noisy. So it's quite hard to tell which of those different projections are we following. And to be honest, they all agree quite closely up until about 2050. If you take an average of all, it's a bit easier. But if you smooth that using a sort of 20-year smooth, this value here, you can see that we're currently tracking sort of towards the mid to upper end of that range. So it gives us fair, in fact, we're very close to this DEFRA 06 projection here. Now, so Currently, we're not rising faster than projected. We're rising at about the rate that the current plan is based on, which is quite a high-end scenario anyway. But one of the interesting things is currently in the plan, we assume that tides aren't going to change dramatically. But what's really interesting is when we look at this data, here I've just taken 5 of the sites where we actually have hourly records. We can start to look at, this is high water, this is low water over time. Now it's quite difficult to see here, but if you look at the difference between the two, tidal range, so Harwich, Tawapia, Southend, Sheerness and Dover, you can see that tides have this 18.6-year cycle called the lunar nodal cycle. But if we remove that cycle, we can see that actually not only is sea level rising, but the tidal range is getting bigger within the Thames at about 1 millimeter per year, comparable with sea level over the 20th century. So not only is sea levels rising, but tides are getting bigger. Now, I was quite lucky to go and meet the Archbishop of Canterbury a few years ago, and he had this painting in Lambeth Palace just across the way. And what you can see here is that the Thames was only about 2 or 3 meters away from Lambeth Palace. But if you look at the Thames now, this was a photo I took, there's at least 50 meters. So we've constrained the Thames, we've deepened the Thames, and we think it's that has caused tidal range to go up. I'm just going to skip over this last slide. So just very quickly, we found that sea levels have risen by about 15 centimeters between 1890 and 1960, another 10 centimeters since that. And the trend has increased up to about 3.3 millimeters over the last decade. We found that not only is sea level rising, but the tide itself is changing. High waters are rising faster than low water, probably because of anthropogenic changes in terms of the constraining of the Thames, the deepening of the Thames. I skipped this over, but we find no significant changes in storm surges in the past 100 years. There's no evidence in the Thames that storm surges themselves have changed. However, extreme sea levels have definitely changed, both as a result of rising sea levels, but also as a result of this changes in tides. There's much more details here in this report. So that's just a very quick snapshot of where we are in the Thames Estuary 100. I'm happy to answer any questions or specific questions people have afterwards. Thank you.
Thank you very much, Ivan. And thank you for entering 2 million data entry points over the past 2 years, keeping us all safe here in London.
No problem.
I saw there was at least one comment online.
Yeah, thank you for the presentation. You probably weren't aware that somebody listening was part of the original team that designed, located, and actually built the barrier. I should advertise that it was all done using foraminifera, which makes it rather unusual. But when the original design was done, the design life was to 2030. And even that design life to 2030 was using what is called the underspill technique of letting water through the barrier, but not sufficient to flood parts of London. So it's really, it worries me because I had a meeting in Parliament with some MPs on the Science Committee, and they seemed absolutely blindly unaware that the design life of the barrier was 2030. And looking at the dates that you've been presenting, which I'm sure are perfectly correct, it strikes me we're asleep on the job, and I just thought we ought to raise that.
What's your surname, Malcolm?
Sorry?
Malcolm Hart.
Malcolm Hart. I'd love to speak to you afterwards, Malcolm, so maybe we could have a phone call. And I worked with Andy Batchelor for many years, who's the head of the barrier. And in fact, I bought a book about the barrier, and I think you signed it. So it's nice to chat to you in person. So yeah, the barrier was never designed to protect West London. And if we continue to protect West London, closing for fluvials, then the end life of the barrier is 2030. Now, there is hope that eventually we'll stop for closing for fluvial closures, and that's partly why the team believe they can extend the life to 2070. But you know, there is a lot of problems, and one of the problems, it's not so much the height of the barrier, it's how much you use the barrier. If you use the barrier more than 50 times a year, there isn't enough time to do maintenance. So actually the lifetime of the barrier is not actually the height, it's how often you close it. We have closed it. We have already closed it 50 times once in 2013, 2014 season. So yeah, it's very, very complicated. And I know the team have some confidence they can extend the life to 2070, but it's going to cost a lot. It's going to involve a lot of maintenance, a lot of other things. But yeah, no, that's a very good point, and thank you for raising that.
Well, it was interesting, and that's probably why I get ignored, that I complained when the barrier opened, because the Queen, late Queen, didn't meet a geologist or an engineer when they opened the barrier. We were all excluded because obviously we're the sort of people who get our hands dirty dealing with cores and boreholes and all that sort of rubbish. But anyway, I'll send you the papers that I've written on the topic, and you might find that interesting.
Yeah, I think I've read all of them, but yeah, no, thank you.
We have no time for more questions, so thank you very much. So as we were speaking about the late Queen, it's an honor for me to introduce the next speaker, Prince Emeka Ndimele from Lagos State University, who will have the next talk. I saw that Emeka was online, so if we could switch to him, please.
Okay, my name is Prince Emeka Ndimele of the Department of Fisheries, Faculty of Science, Lagos State University, Lagos State in Nigeria. And my topic today is vulnerability, resilience, and adaptation of Lagos coastal community to flooding. By way of introduction, we'll first look at Lagos. Lagos is a metropolitan city. It is Nigeria's economic and political capital. It was the capital of Nigeria until 1991, when the seat of power, or the capital city, was moved to Abuja, but it still remains the economic hub of the nation. The state has about 10% of the total population of Nigeria. Nigeria is about 200 million people, so Lagos is roughly 20 million persons in less than 4,000 square kilometers, less than 4,000 square kilometers. It has about 60% of the non-oil revenue, and every ethnic group in the country is represented in Lagos City. Many parts of Lagos City are spread over Barrier Island or in close proximity to seafront and the edges of Lagos Lagoon. Actually, we have what is called the Lagos Lagoon Complex, which is a system of lagoons in Lagos State, comprising of about 4 to 5 lagoons: Lagos Lagoon, Epe Lagoon, Ologe Lagoon, Lekki Lagoon. Those 4 lagoon system is what we call the Lagos Lagoon Complex. But the Lagos Lagoon itself is quite massive, and it is connected to the sea by a number of channels. Lagos comprises of settlement that has grown from predominantly farming and fishing villages to highly urbanized cities. Although we still have relics of farming and fishing in the area, because it's an island that is surrounded by water, different marine, freshwater, and even brackish water. It is regarded as one of the fastest growing coastal cities exposed to climate change because of its coastal terrain, its rapid population growth, which presently stands at about 3.5% per annum, and it has a lot of anthropogenic activities. As a matter of fact, Lagos accounts for about 60% of industrial establishments in Nigeria, which has led to frequent experience of flooding and storm surges. This slide looks at Lagos vulnerability. Lagos has a landmass of about 3,577 square kilometers, with a population of more than 20 million people sitting on that less than 4,000 square kilometers. If you do your calculation, you see the population density, quite massive. and water wetland covering more than 40% of the total landmass. So the 3,577 square kilometers, about 40% or more, is made up of water of different types, including wetlands. Despite the high population of middle income earners, the vulnerability of the negative impact of climate change has constantly threatened the survival of people in Lagos State. And that is understandable because it's a city that is sitting very close to marine ecosystem. It's very populous, and so the challenges of flooding is something that we see almost every time. Lagos multi-dimensional flood risk profile. The entire region lies 100 meters below sea level, and the city sits on swampy mangrove and largely waterlogged soils with a high water table. All these features make Lagos vulnerable to flooding. We have mangrove on the fringes of the whole of the Lagos Lagoon system. And it's not only in Lagos that we have mangrove in Nigeria. As a matter of fact, Nigeria is the second or third largest stock of mangrove all over the world, behind Indonesia and I think one other country. We have large stock of red mangrove, Rhizophora resmosa. But the problem is that these mangrove are often destroyed by petroleum exploration, and then they look as to convert this mangrove and use them for firewood. That's part of the challenges you have. Water bodies, lagoon, creeks, and wetland cover over 60% of the land area, and additional 12% subject to seasonal flooding. So we have key categories of flood risk in Lagos. We have rainfall, flooding, we have fluvial flooding, coastal flooding, and exposure to multi-hazard risks. Adverse effects of flooding. There are different risks associated with flooding, or Lagos as a state is exposed to different types of risks. I'll put them in four categories first, four categories first, before I run through what I have on my slide. The first one is loss of farmland and livestock. When there is flooding, a whole large expanse of land, agricultural land and livestock can be wiped off by flood. And then you can begin to imagine the ramifications of the challenges that locals will face. Because most of the people who face this problem are farmers, the locals. They're very vulnerable, women, children, who depend primarily on farming as a means of livelihood. So the moment the farm is wiped off by flood, then there is problem of food scarcity, problem of economic problem because their sort of livelihood has been damaged, and other problems could arise. And that is why we have a lot of people in rural area below the poverty line. Another problem caused by flooding is destruction of property. Properties can be destroyed by flooding. There was a major incident in July 2011 in Lagos State. There was rainfall for 6 consecutive hours non-stop. As a matter of fact, that day I thought this world was going to come to an end because I was not at home, I was in church, and I had to stand at a place for 6 hours waiting for the rain to stop. I have never had that kind of experience before. Because the experience I have about rain is that rain will fall, subside, then fall, subside. It will just be intermittent. But this was 6 hours of continuous downpour, and areas that were not initially flooded in Lagos became flooded. So Lagos is seriously prone to flooding. And then there could also be deterioration of health as a result of waterborne disease caused by flooding. Then life could also be lost. I'm going to mention some problems that we've had in 2020 and 2022, the recent incidences of flooding in Lagos. But stating it specifically, to run through what I have on the slide, the impact of flooding is particularly significant because Lagos State is surrounded by aquatic ecosystem, fresh, brackish, and marine, and its low elevation and topography increases its susceptibility to flooding. Experts and analysts say that incident of incessant flood in Lagos presents danger as the city prepares or is not prepared for the projected sea rise. And that is not peculiar to Lagos only, it is peculiar to the low-income country because oftentimes we are not fully prepared for flooding and other weather events. In particular, we are not prepared. The people are not even prepared for it. We do not have the technology to predict this event, and so it takes us unaware, and oftentimes the damage are best imagined. The sea level rise is expected by 2 meters at the end of the century, putting Lagos with a low topography at a risk of completely sinking. This is possible because we had part of Lagos sink previously, because Lagos is close to the Atlantic. So if once there is any kind of flooding, there's a place called Victoria Island in Lagos, it could easily sink. Wetland that could act as buffer against the flood action are constantly destroyed, and such areas are converted to residential or industrial. Yes, this has been happening, but I think Lagos State government is taking a very pragmatic step in ensuring that some areas are dedicated wetlands, that the government try to maintain it in its pristine form. That's what the government has been doing lately. These have contributed to the instability of Lagos ecosystem and a reduction in the ecosystem services supplied by these ecosystems. Furthermore, flooding is one of the key factors that have prevented Africa's growing urban population from escaping poverty. Because we don't have the facility to predict and so prepare for flooding and other hazardous weather events. It takes us unaware, and it drives a lot of people into poverty because oftentimes the most vulnerable are the locals, and they sink deeper into the poverty sector. It impedes the achievement of sustainable development goals. I've mentioned about 5 here: SDG 1, no poverty; SDG 2, zero hunger; SDG 3, good health and well-being; SDG 6, clean water and sanitation; SDG 11, sustainable cities and communities; SDG 13, climate action. Flooding has negative impact on some of these SDGs. This is due to the fact that many African cities lack resources and infrastructure needed to withstand extreme weather conditions. Surviving in flood-prone cities like Lagos is a daunting task because flood affects livelihood, affects health, and can even cause death. Now, specifically speaking about the 2020 flood, it affected about 40% of the local governments in Nigeria. Nigeria has about 777 local governments, and so it affected about 40%. That is roughly about 300 local governments were affected. 97% of the states were affected. We have 36 states, and Abuja, the federal capital territory, 37. So about 36 states, 35 to 36 states were affected. It displaced about 120%. So it also increased the problem of internally displaced persons in the country. 120 persons were displaced. And then we recorded a mortality of about 68%, aside from properties and farmlands that were destroyed. But in 2022, just last year, the flood surpassed the previous episode if the mortality figure is anything to go by. As at the time this report was made, the mortality figure stood at about 600 compared to the one of 2020, which was just 68. This is a graphic picture of flooding in Lagos State. What we have on the left is not a serious flood event. Not a serious flood event. If it's a serious flood event, the area will be impassable. It will be unmotorable. People will not even want to take the risk of flying a seriously flooded area. And then to the right is another flooded area in Lagos Lagoon. If you look closely at the structure there, it shows residential area. Sounds funny, but residential area. What we tell you that is a residential area. If you look closely at the side of the figure on the right, you see clothes hang, which means people live in that area. People live there, and the wood can even be firewood or fuel wood or wood for construction of boats. So between 2011 and now, flood have resulted in the destruction of over $10 billion worth of assets and have affected over 7.7 million people in Nigeria. Now, this slide shows flood resilience cycle and the 6 cardinal points: adaptive processes, planning and development, integrated catchment management, social network, cross-sectional society role, strategic governance. There are 2 circles. The outer circle is what I've titled PPRR: prevention, preparation, response, recovery. And it is cyclical, because you start from prevention. You try to put up structures, infrastructures, advocacy, and try to prevent flooding. In the case that the flooding cannot be prevented, then you now begin to prepare for the flooding proper. You need to prepare for the incident of flooding. And then if you are properly prepared, the impact will not be as damaging, as destructive as when you are not prepared at all. So after preparation, what comes next is your response in the event of flooding. If there's flooding, how do you respond to flooding? After beyond response, we now talk about recovery, because when there is flooding and you have responded to flooding, given your capacity, the next thing is to talk about how to recover from the flood and then see the possibility of preventing a future occurrence. Significance of flood resilience: less expensive flood recovery, ensure adequate preparedness for flood events, limiting the adverse impact of flood, ensuring quick recovery of the affected community, and then limited impact on natural resources. These are the significance or importance of flood resilience. If we decide to take action, then it will reduce the impact of flooding if it is not preventable. What has Lagos State government done in the past 2 decades or thereabout to help in flood control and management? In 1999, they improved coordination and management of disasters. The federal government and the National Emergency Relief Agency, now NEMA, established emergency management agencies at national, state, and local level. That means establishing emergency management agencies at national, state, and local level to manage the incidents of flood and other hazardous weather events. Between 2007 and 2011, Lagos State boosted capacity, improved flooding mitigation and planning. The Ministry of the Environment increased the number of engineers and staff in the Office of Drainage Services from 5 to 57. And then in 2009, the state also enhanced data quality on flood risk trend, topographic mapping with radar and GIS-based analysis undertaken by Lagos State government. This built on the growing role of 3 agencies. The 3 agencies, NASRA, NIMET. NASRA is for, NIMET is for meteorological, and NASRA is for weather services.
Mika, we're running a bit over time, so.
How many minutes do I have left?
3 minutes.
3 minutes, okay. We also have actions taken in 2006 to 2013. There were actions taken in 2010 in Lagos State government discontinued physical development in many areas liable to flooding and wetland. And in 2019, there were also actions taken. The state government and the Rockefeller Foundation established 100 resilient cities. Then this figure looks at the adaptive capacity of living communities to vulnerability and exposure to climate change. Because of time, I will not dwell so much on it, but there are adaptability at different levels, at individual level, at community level, at regional, national, and global level. And then finally, adaptation strategies to help reduce flood in Lagos State. The first thing is, in terms of adaptation, the focus has been on improving water system and flow through clearing and clogging of drainage channels, shoreline protection, and erosion control. In addition to this measure, the government of Lagos State launched the Lagos International Climate Change Summit in 2009 to bring together researchers and practitioners and climate change experts to deliberate annually on the impact of climate change on the Lagos ecosystem. The summit has grown since, and its fifth edition was held in March 2013 at the Eco Hotel. Individuals and corporate organizations in Lagos State have also joined the climate change campaign, some partnering with government to reduce impact from flooding, storm surges, and potential sea level rise. Finally, my recommended adaptation strategy: apply green infrastructure strategy, consider stormwater logistics, construct new infrastructure that can withstand flooding and other hazardous weather events, maintain and restore wetland. Very important, because there are so many wetlands in Lagos State. We can maintain a whole lot of them and restore those ones that have been degraded. It will help to mitigate the impact of flooding. Maintain water quality and availability, model climate risk. I've listened to some presentation. I think we're going to learn a bit from this, because if we can model climate risk, it will help us to adapt better, because we know when these problems are likely going to happen, are likely to occur, then we know what actions to take to prevent the occurrence or mitigate their effects. Modify land use, plan for climate change, preserve coastal and land development, monitor operational activities. I want to thank everybody for your rapt attention. Thank you so much.
Yeah, we can hear you. Thank you, Mika. I must say, from my perspective, thank you very much for a very eye-opening perspective on a different part of the world that we've not heard about much before, where flood risk is very much an everyday risk. So thank you very much. Unfortunately, we don't have time for any more questions. So I would like to invite the next speaker, Stephen Hencher. Please come forward. Okay. Welcome back, everyone. We're about to start with the final talk for the conference. We're diving a little bit back into the past, given the time difference and availability of our final speaker. I would like to give the mic, or virtually at least, to Rob de Conto. If we could change over to him, please. Thank you.
Is that working?
Yes, it does.
Perfect.
Go ahead.
Great. Thanks, everyone. And I'm sorry I can't be there in person. Thanks, Ed Gasson, for giving me a title to the talk. I think Ed wanted me to provide a broad paleo perspective with a focus on Antarctica and its sensitivity to future warming. So I'm going to show some work that some of you will be familiar with and a few new things. With an outline like this, just a few words about why Antarctica and why that focus. It's been a large part of what I've been working on over the last decade or more. And then we're going to look at the past sensitivity of the ice sheet to a given amount of warming relative to the current modern situation. So this is a way to sort of bridge a paleo perspective on what we might expect into the future. The third bullet is something I think I'm going to have time to sneak in, and that's just to just remind everyone that as we are developing these really critical records of global mean sea level change, we ultimately really would like better information and higher confidence about the relative contributions of both ice sheets. So I'm going to just say a few words about the possibility of interhemispheric anti-phasing of the two ice sheets, and the fact that Greenland and Antarctica in the past at times can be out of phase and at other times perhaps in phase, which has major implications when we try to constrain or to quantify the sensitivity of one ice sheet or the other to a given amount of warming, which of course is going to be important moving into the future. So, just the big picture background. There's an awful lot of potential sea level rise locked up in Antarctica. The ice above flotation has a volume about 8 times that of Greenland. But with that said, Greenland today is contributing roughly twice the pace of relative contribution to sea level rise relative to Antarctica. So Greenland today is a larger contributor. So, you know, given the enormous size of the Antarctic ice sheet, where even a very small fractional change in the system could have really dramatic implications for coastlines and low-lying places all over the world, the question is, you know, could Antarctica actually begin to outpace Greenland as the dominant contributor to sea level rise in the future? Today, the processes that are dominating Greenland's contribution to sea level rise, and which happens to be happening at an accelerating pace, are mainly related to surface processes around the fringes of the ice sheet in the lower altitudes where air temperatures are relatively warm, whereas the places where Antarctica is beginning to increase its mass loss and its delivery of ice to the ocean seems to be driven by dynamical processes within the ice sheet, and in particular, places where the ice sheet is interacting directly with the ocean. So, you know, we're worried about Greenland for sure. The pace of mass loss on Greenland is, like I said, it's accelerating as the ice sheet itself loses mass and its surface elevation lowers into warmer reaches of the atmosphere. We expect the melt to accelerate as there's more meltwater and even biological activity on the surface of the ice. The ice surface is getting darker. There's debris and dust melting out of the ice at the surface, contributing to the darkening of the ice sheet that is you know, causing relatively impressive rates of meltwater, and some of that meltwater is making it to the ocean and rising sea level. But the Greenland ice sheet is really just so fundamentally different as a system relative to the Antarctic ice sheet. So this is just a plot with the two green dominated panels on the left showing the current bathymetry of Greenland versus Antarctica on the bottom left. And on the right, you can see the ice sheet sitting on that bathymetry, and the colors from blue to reds are showing the speed of the ice. And you can see in Greenland that the ice that is actually reaching the ocean is flowing in, you know, in fast streaming glaciers, big outlet glaciers, roughly maybe on average 5 to 10 kilometers wide, streaming in fjordal systems. But a lot of the ice sheet margin in Greenland is actually terrestrial based. And you can see that on the left-hand plot, just showing the bathymetry, that a lot of the Greenland margin is actually terrestrial, where even, you know, given the ice sheet that's sitting on Greenland today, a lot of that land surface is actually above sea level. Now, if we look to Antarctica, where the much bigger ice sheet is sitting, you can see a lot of the area underneath the ice sheet is in blues, and some of those blues are quite dark, more than 2 kilometers below sea level. And roughly about a third of the ice sheet is actually sitting on bedrock that is below sea level today, and again, in some places reaching 2.5 or more kilometers below sea level in places, for example, under the heart of the West Antarctic ice sheet. So the fringes of a lot of the Antarctic ice sheet are interacting with the ocean and are directly in contact with ocean waters that can actually sort of attack the ice both from the bottom up, you know, as well as atmospheric warming actually contributing to processes at the surface that can be impactful. So very, very different systems. Now, Antarctica's ice that is sitting in these deep basins below sea level today, in many places is supported by fast flowing, floating extensions of the glacial ice that we call ice shelves. And most of the places here, these red colors where the ice is flowing fast, this is ice that's actually floating on the ocean surface. And some of those arrows are pointing to some of the major ice shelves. And why they're so important and why they really represent, I would say, a potential tipping point in Antarctica's future is that they play a fundamental role in the dynamics of the ice that is upstream, sitting on the continent itself. So if we have a big, thick piece of the ice sheet resting on bedrock that is below sea level, and in this case, the actual surface is sloping away from the ocean in toward the continental interior. This is representative in this cartoon of the Thwaites Glacier. The ice is flowing from left to right toward the sea. We have snow falling on the ice sheet. The ice is flowing under its own weight out toward the ocean. And the ocean is relatively cold, and that ice doesn't instantaneously melt. It begins to float once the ice gets thin enough as it extends out into the ocean. This is our floating ice shelf. Now, if the ice shelf touches down on, for example, some bathymetric features under the seafloor, or it scrapes along the edges of, for example, a fjord or a big embayment in a bay, then this ice shelf, even though it's mostly floating, it can still provide some structural support or a back stress, we call that buttressing, that slows the flow of the ice from the ice sheet out into the ocean, and potentially provide some structural support that would, in this case, slows calving or the breaking of ice at the ice sheet edge. And, you know, this is sort of the kind of analogous to a flying buttress on a Gothic cathedral would be an example of engineering trying to replicate that sort of support. So, you know, thinking about a future where those ice shelves might either thin, lift off of their grounding pinning points, we call them, places where those ice shelves actually touch down on the seafloor. And what that might do, there have been a couple of different potential speed ups in the delivery of ice, Antarctic ice to the ocean, triggered by that loss of ice shelves. And the first has become known as the marine ice sheet instability, where we initially have a nice, healthy ice shelf, maybe touching down on the seafloor, providing some back stress, and either through the ocean, thinning that ice shelf from below, maybe an increase in calving of that ice shelf, the ice shelf begins to thin, provides less buttressing, allowing more ice to flow out into the ocean. And if the edge of the ice sheet starts to back into a deeper and deeper basin below sea level, where you can see there's a retrograde slope on the subglacial bedrock, as the ice retreats back into that deeper basin, the thickness of the ice, just at the point where it's beginning to float, we call this the grounding line, the thickness of that grounding line is getting thicker. The ice is getting thicker at the grounding line as it backs into one of these deep basins. And it turns out that the flow of the ice, the flux of the ice from the ice sheet through the grounding line out into the ocean is very strongly dependent on the thickness of that grounding line. So this provides a positive feedback and a potential acceleration in the pace of ice loss through a thickening grounding line as the ice sheet retreats into a deep basin. Now, the processes related to the marine ice sheet instability on the left are mainly, you know, a response to the ductile processes of ice, its creep, its flow, and sliding at the base of the base of the ice sheet. Now, there could be something else that we need to worry about in Antarctica, and that's related to the fact that if the ice sheet is suddenly, for example, loses an ice shelf, then it's potentially going to lose its buttressing support that could expose the edge of the ice sheet itself in a way that creates a lot of stress within the ice. And those stresses actually could potentially exceed the material strength of the ice itself. And we might expect a speed up in the pace of iceberg production or calving. And this process has been coined the marine ice cliff instability. Now, and this point will come up again in a few minutes, but most of the existing ice sheet models that we are using today for predictions about the Antarctic ice sheet's response in the future do a really wonderful job of representing these processes, these physical processes in the system. And to date, just a few modeling groups are exploring the potential role of a speed up in the calving, the breaking, the brittle processes in ice sheet models that actually could deliver even faster ice loss than the marine ice sheet instability caused by the ductile and the sliding processes. So this is really wonderful work of Guy Paxman's, who's done a wonderful job of trying to recreate what Antarctica looked like in the geologic past relative to how it looks today. And through tectonic processes, thermal subsidence in places, uplift in a few others, and glacial erosion of the continent, if we try to reconstruct the continent back in time, and these are isostatically equilibrated bathymetries or topographies in this case, all the land in brown that's actually above sea level. This is going back to around the time that the initial ice sheet formed around the Eocene-Oligocene boundary versus the Pliocene. And you can see that there's a lot of blue here, and it's pretty clear that West Antarctica in particular, as well as some deep basins in East Antarctica, have been getting deeper through geologic time, leading up to a configuration today where actually the bathymetry is at its deepest point in West Antarctica, for example, and in these East Antarctic basins versus essentially the continent's whole Cenozoic history. This is a departure in the bathymetry. And so you can see the greens and the blues are deeper than today. This is the Pliocene relative to modern. And you can see again that most of West Antarctica actually, even just over the last few million years, has deepened considerably. And that, as the work of people like Flo Coglioni, who we heard from earlier today, and Ed Gasson has been working on this, have demonstrated that this change in the geology itself has actually increased the sensitivity of the ice sheet because of those instability processes that have to do a lot with the bathymetry, what the geometry of the bedrock looks like, the marine ice sheet, and potentially the marine ice cliff instability. The ice sheet has potentially been increasing in its sensitivity to warming through time. So what we're going to look at now is just some fun experiments where we spin up the ice sheet. We try to get it very close to an equilibrium state where it's not gaining or not losing much mass, representing snapshots in the geologic past. And so the representative time slices we're going to look at are a Pliocene ice sheet, mid-Pliocene representation of the ice sheet. So here, this is a Pliocene climatology using an ice sheet model that we use for future projections with all the bells and whistles and the physics that we use for making future projections. Here's a last interglacial ice sheet example representing the ice sheet with a climatology we're trying to represent 125,000 years ago. Here's an LGM ice sheet, so a colder climate state than today, and here's modern. And what I've superposed here are these yellow and red colors, and this is showing the bathymetry, the depth of the ice sheet, the base of the ice below sea level, beginning at 750 meters below sea level and extending even deeper. And so this is just highlighting where the really thick ice and where that really deep bedrock, where those deep basins are, in some cases with reverse slope beds that could potentially spark these instabilities in the ice sheet if the ice sheet loses enough of its buttressing ice shelf support. And, one thing to just highlight is, yes, the LGM ice sheet in general is thicker, but you can see the deep basins are actually away from the paleogrounding line of the ice sheet. The modern configuration is the configuration of the ice sheet where we have that really deep bedrock with reverse slopes in places, both in West and East Antarctica, pretty close to the contemporary grounding line. So these are initial states representing these time slices. And what we're going to do is we're going to apply some warming. And the way that we're going to do that is we're just going to add some warming to the uniform atmospheric temperatures and to the subsurface ocean temperatures by a given amount. And I'll show you that in just a second. Now, these are the spun up quasi-equilibrated states of the ice sheet under these different conditions: Pliocene, last interglacial, last glacial maximum, and modern. And so these are the equivalent sea levels in this is the ice volume representing these equivalent sea levels with these different states. Now, there are two versions of the model that we're going to look at. One is the version that has all of the marine ice sheet instability, the ductile processes, and the other version of the ice sheet model accounts for these brittle ductile processes, whereby if ice shelves become warm enough on their surface to be covered with meltwater, surface crevasses penetrate deeper and deeper into the ice shelf starts to break up, the buttressing is lost, and then calving accelerates. And the thicker the ice is that's unbuttressed with no structural support, the faster the calving increases. Okay, and so here are the departures in these ice sheet states relative to modern. Now, one quick thing to point out, kind of interestingly, is that the Pliocene ice sheet is only 1.4 meters of equivalent sea level smaller than the modern. And, people like Georgia Grant, who I heard George's voice in the audience, I know George is there, which is great, have been working on, okay, how much higher was sea level during the Pliocene? Ken Miller also, this is a very small number. When we add these brittle processes to the ice sheet models, we get into a range of changes in sea level that might be a little bit closer to what the geological community is suggesting. This is just to demonstrate that after, it took me a long time to get these ice sheet states spun up to be pretty close to equilibrium. These are the modern LGM, last interglacial and Pliocene ice sheet states run for 500 years with no change in the climate forcing. And you can see that, we don't have a big change or drift in the size of the ice sheet. But interestingly, the modern ice sheet state, after 500 years of running the modern ice sheet into the future with no change, with modern climate forcing, we see after a few centuries that we actually start to see a little bit of an uptick in the pace of mass loss. And that's because the Thwaites Glacier in West Antarctica, which is retreating onto deeper and deeper bedrock after 5 centuries, is actually beginning to speed up in its pace of retreat. So what we're going to do is, instead of running forward for 500 years, 5 centuries into the future with no change in the climate state, we're going to take these different initial conditions, modern, last glacial maximum, last interglacial, and Pliocene, and we're going to just apply either 1, 2, 3, 4, 5, up to 10 degrees Celsius of warming in the atmosphere, and half that amount of warming in the subsurface ocean. The subsurface ocean temperatures, again, are important because they can attack the buttressing ice shelves from below, making them thinner and reducing some buttressing. And we're going to see what happens. And interestingly, what we find is the modern, so what these plots here are showing, these line graphs, are the change. This is the rate of sea level contribution from the Antarctic ice sheet for the modern, last glacial maximum, last interglacial, or Pliocene for a given amount of warming. So this top left plot, this is adding 1 degree Celsius of atmosphere warming, half a degree Celsius to ocean warming on to the modern conditions of the ice sheet. And you can see far and away that the modern ice sheet with that 1 degree of warming produces the fastest pace of ice loss. And this is the cumulative sea level contribution over those 5 centuries in the modern case relative to these paleo examples. We do the same thing for 5 degrees. And again, the blue curve, highest peak in the pace of mass loss. 10 degrees C, all the ice sheets actually pretty close to contributing roughly the same pace of mass loss. You could argue that the modern ice sheet actually is the fastest. When we add the brittle processes, the calving processes accelerated by the loss of buttressing, it's the same story. The modern ice sheet in blue, the modern ice sheet in blue, the modern ice sheet in blue. And if we rank 20 different simulations, both 10 without these brittle processes added to the ice sheet models and 10 with the brittle processes added, and we rank them, we find that the modern ice sheet 18 out of the 20 simulations produces the fastest pace of ice loss. Now, this is kind of fun in that the last interglacial scenario jumps from coming in last, basically being the slowest contributor to sea level, to the second fastest contributor to sea level when we add these ice cliff calving processes. And the reason is that when we add those calving processes, we increase the sensitivity of the East Antarctic basins, because in the last interglacial, in these simulations here in the top left, without those brittle processes, the East Antarctic basins haven't retreated much. And so there's some vulnerable ice, very, very deep channels into these basins that become vulnerable when we add these brittle processes to the ice sheet models. So the bottom line is that, relative to at least those examples of the ice sheet in the past, the modern configuration of the ice sheet, the combination of the bedrock evolution and the current climate state, the atmosphere and ocean temperatures that we see today, make the ice sheet more vulnerable than these paleo examples. And if we look, for example, at the evolution of the bathymetry just since the Pliocene, and we either use a modern bathymetry versus a Pliocene bathymetry, we find that the modern bathymetry increases the sensitivity again to the pace of retreat, faster retreat, more vulnerable, even that just recent geological evolution of the bedrock. In fact, with 5 degrees of warming, we see, depending on whether or not we include the extra calving processes, we see between 10 and about a 25% uptick in the pace of ice loss, just as a function of the evolution of the bedrock of Antarctica. So, I'll be closing in on, there's been a lot of confusion about, the motivation for adding some of these calving processes, the brittle fracture processes, the so-called marine ice cliff instability, into ice sheet models. But to be clear, this is ultimately, I've heard people say, well, Rob and his colleagues, Dave Pollard and Richard Alley, they've been adding these processes to ice sheet models because it's letting them match the geologic records. Well, in fact, we're using the geologic records to tune and calibrate the representation of these processes in the models. But the processes are really driven by first principles. So a really wonderful paper by Jeremy Basis made it very clear that if you have a big, a thick column of ice with no buttressing support from an ice shelf, and that ice is thick enough so that it has an ice cliff above the surface of the water, that you're going to end up producing stresses in the vicinity of that ice cliff that theoretically are going to exceed the toughness of the ice itself, and it will fail. Now, the actual mode and the details of failure, the actual details of the precise calving processes, which I'm going to be talking about in a more technical glaciological talk tomorrow with Ed and a few other folks, is borne out in things that we've actually observed today. This is where the Larsen B ice shelf used to be back in 2002. It broke up in dramatic fashion after the ice shelf became covered with meltwater and exposed outlet glaciers like the Crane Glacier, to a complete, almost instantaneous loss of buttressing. And when that happened, 2 things happened to the glacier itself. The glacier started to flow faster toward the ocean, in this case by about a factor of 3. And even though it sped up, it began to retreat very rapidly back into the ice sheet itself. Now, we have a few snapshots of examples of those processes happening today. We see some very thick outlet glaciers in Greenland, like the Jakobshavn Glacier, contributing, the equivalent of 13 kilometers of ice, of wastage rate or a calving rate. The Jakobshavn Glacier is flowing toward the ocean between 10 and 12 kilometers a year. And at the same time, it's been backing up into the ice sheet itself because the calving is happening at such a fast rate. So this is just an an example of a parameterization for calving represented in a model where we look at the stresses at the front of an ice sheet where the ice sheet has lost its buttressing ice shelf and it has exposed an ice cliff. There might be some crevasses, both poking down from the surface and poking up from the base, which reduces the thickness of the ice that can support the stresses at the ice front, more crevassing, higher stress. And at some point we reach a threshold in that height of the cliff where we say, okay, there's going to be some calving happening at that ice margin. And we can ramp up that rate of calving represented by these lines increasing. So this is calving wastage rate on the y-axis as a function of the stress that's related to the cliff height. And we can say, okay, well, what do we recognize today? We recognize the possibility for calving wastage rates on the order of 13 kilometers per year, like we see in Greenland today. But we can say maybe the maximum rate of calving is somewhat less than what we see on Greenland today. And so we can produce many, many versions of an ice sheet model with these different parameterizations for calving and for the sensitivity of crevassing to meltwater on the surface once it gets warm enough in the summertime to start having temperatures above freezing. We can run hundreds of simulations with slightly different physics representing these brittle processes. And we can compare those simulations, for example, over the modern era to satellite information about the pace of ice loss. And what we find is, here's an example of hundreds of simulations of an ice sheet model with very different representations of these brittle processes. We are looking at the rate of ice loss relative to observations over, for example, the IMBY era over the early 21st century. And we find that most of the ice sheet models reproduce the modern rate of ice loss in West Antarctica, for example. But that doesn't really provide us great guidance because these are all very, very different versions and sensitivities of the ice sheet model, which is why we turn to the paleo records. We look at the last interglacial and we can see which versions of the ice sheet model will match our best targets for what we think last interglacial sea level was. We could do the same thing for the Pliocene. And by doing so, we can start to eliminate versions of the ice sheet model. Now, what's critical here is that, I'm relying on an estimate of what Antarctica's contribution to last interglacial and Pliocene sea level was. The results are profound because, these are simulations of a future, these are future simulations with an ice sheet model without these brittle processes, even under a really high emission scenario going out over 3 centuries. And we can see that in this simulation without those processes, the East Antarctic ice sheet, this blue line, gains a little mass because it's warmer climate, more precipitation, more snowfall. The West Antarctica retreats, but a relatively modest contribution to global mean sea level. When we add these brittle processes that are calibrated based on estimates of last interglacial and Pliocene sea level, like people like Georgia Grant are trying to develop, we see a simulation that looks like this, but still with a huge range of uncertainty around those estimates. The fastest pace of ice sheet loss in this RCP 8.5 simulation has a speed limit. And the speed limit that's imposed is we say that the glaciers in Antarctica can never do anything faster than the Greenland outlet glaciers. And so I just want to, drive home the point that the paleo records are providing some constraints. We're trying to do a better job of minimizing this huge uncertainty around some central estimate. But the tail of this distribution, like this simulation, is 15 meters by the year 2300, should not be considered an upper bound of what's actually possible. So lastly, I'm thrilled to, see a conference like this that is sort of linking up knowledge about the geologic past and thinking about what it might be able to do to inform the future. Global mean sea level is really important to know, but like I said at the beginning, in the outset of this talk, really what I want to know is how much did the Antarctic ice sheet contribute to sea level rise with a given amount of climate forcing? And, you know, I've long been intrigued by the possibility, and this has been borne out by some work, like Bas de Boer did some really great early work on this, looking at the possibility of Greenland hiding some global mean sea level that would be contributed by Antarctica at times in the geologic past. So if you think about the precession timescale forcing of changes in the Greenland ice sheet during, for example, the Pliocene, where maybe during a warm climate, Greenland is mostly gone. But then, you know, 10,000 years later, halfway through a precession cycle now, things have cooled down in the Northern Hemisphere. That maybe 5 or 7 meters of potential sea level locked up on Greenland would be masking 5 to 7 meters of potential sea level rise coming from the Antarctic ice sheet when we're just looking at global mean sea level records. So I just want to end on these kind of fun simulations that I just ran literally last week in playing around with some idealized orbital cycles where there's sinusoidal temperature forcing. Now we're looking at the Greenland ice sheet, just to see what Greenland actually would do in a warming followed by a subsequent cooling. And again, this is not a, you know, sawtooth shaped sort of climatology, just very sinusoidal, either plus or minus 7.5 degrees of warming and then cooling, or a little bit less, plus 5 degrees, or plus 2.5 degrees. And what we find is, with a lot of warming and a lot of subsequent cooling, the Greenland ice sheet disappears after about 4 millennia. It stays, there's no ice on the Greenland continent. And then eventually it gets cold enough and the ice sheet is actually able to recover within half of a precession cycle. A little bit less warming, plus or minus 5 degrees. So a sinusoidal warming of 5 degrees in the atmosphere. And by the way, half as much warming in the ocean, followed by cooling. And we see this sort of shape. Again, this is just plus or minus 5 degrees Celsius and only plus or minus 2.5 degrees Celsius of the ocean temperatures. Complete collapse of the ice sheet. It takes longer. It takes 6 millennia rather than 4, but the ice sheet is essentially able to almost completely recover, again, within 1/2 of a precession timescale. These different simulations are representing uncertainties in the bedrock response, the uplift, the viscosity of the mantle under Greenland, and the thickness of the lithosphere. But the main point I'm just trying to make is that you can see that there's significant potential for Greenland to be out of phase, I would say, with Antarctica. So we need to be really careful when we use these geological constraints that are ultimately founded on global mean sea level change estimates to constrain the model physics that we use for future simulations. So I'll end with this slide. You know, just this is from the summary for policymakers from the AR6, and you know, in regular sort of IPCC parlance, they provide some projections of future sea level with a central estimate with these solid lines representing different emission scenarios moving out into the future. And the bounds in this case around those different lines are the so-called likely range, the 17 to 83rd percentile of these projections. And then they show this dashed red line that you can see is way above the likely range of the SSP 8.5, so the warmest emission scenario that they looked at. They call it a low likelihood, high impact storyline. And what this line is that they've taken all the contributions to sea level rise from mountain glaciers, from land water storage, from thermal expansion, ocean dynamics, and so forth. And they've replaced the Antarctic and the Greenland projections of future sea level based on structured expert judgment and simulations from an ice sheet model with the brittle ice cliff calving mechanisms that we just talked about. And, you know, they end up with something like this. This is the 83rd percentile, including those brittle processes. And, you know, this has been conflated with this, what is physically possible. And this is not the upper bound of what's possible. This is, you know, essentially taking, you know, the simulations that are limited by saying that the Greenland ice sheet or the Antarctic ice sheet could never contribute anything faster at its outlet glaciers than the Greenland ice sheet does today. And I have been a little bit uncomfortable with this language somewhat, because using the term low likelihood, you know, implies that we know something about the likelihood. And I think maybe the better message here is that we don't know what the likelihood is what this should, the message should be. It's not that deep uncertainty in this case is the same thing as low likelihood. The deep uncertainty means that we don't know what the likelihood is for something like this, or even something much higher. And I will stop there.
Thank you, Rob. I received a question in the online Q&A here, and I'll just read it out loud for you. Submitted by an anonymous attendee. So an off-the-wall question. A few years ago, some group suggested submarine volcanism might be responsible for West Antarctic ice melting. Is that still considered to be possible?
You know, I think limited scale volcanism has a limited amount of impact on the ice sheet, but I think more importantly is the impact that warm, low viscosity mantle under West Antarctica, relatively thin lithosphere, can have on the ice sheet, actually potentially slowing its future retreat. And so, you know, a lot of research is being done now, and I'm going to be talking about some of this in a related session with Ed and others focused on the Pliocene tomorrow, in looking at different treatments of that low viscosity mantle under West Antarctica and its ability to actually slow retreat. Yeah, so right now, most of the ice sheet models point to West Antarctica as being the most vulnerable. If we warm our ice sheet models by a uniform amount, both in the ocean and the atmosphere, it's that really big, broad, bowl-shaped basin sitting under the core of the West Antarctic ice sheet that is the first to retreat. But, you know, interestingly, maybe there's another story, and that becomes important to pinpoint whether or not it's West Antarctica or maybe the East Antarctic basins that have contributed to these past changes in sea level rise, particularly when we're using GIA fingerprints to say something about West Antarctica versus East Antarctic contributions to past sea level rise. We're not representing individual volcanoes in the models, at least at this point.
Okay, thank you. Any more questions from people within the room?
Can you say something about the influence of the incised valley underneath the Antarctic ice on the speed of ice retreat?
Boy, so which valley? I mean, under West Antarctica, the Bentley Trough extends below 2.5 kilometers below sea level. And it is when the ice margin reaches that really, really deep ice that's when the fastest pace of ice sheet changes occur. And you might be able to see it in, in some of, let's see, these simple experiments. So for example, for the modern. So this peak in the pace of ice loss here, if I was showing you a little animation or a map of the Antarctic ice sheet, you would see that this is when the ice sheet is retreating. The ice margin has retreated now into the deepest part of that trough, which is sort of up into the deep reaches of the Thwaites glacier system today. And the reason why you're getting the fastest rate of ice loss there is that we have reverse slope bedrock. So we have that marine ice sheet instability kicking in, and the ice is very thick, and it would have a high freeboard above the ocean surface, a lot of stress, which means that the calving in the model increases quite a bit. And you can actually see it in, so here's the beginning of a simulation like that. And we're concentrating on this, sector of the ice sheet. You can see the dark blues are where that really, really deep incised trough is deep in the heart of the West Antarctic ice sheet. This is the year 2100. And what's happening is the edge of the ice is now retreating back onto that deeper bedrock. The ice is getting thicker. The bedrock is reversed in slope. And as every year goes by, the grounding line is retreated onto deeper and deeper bedrock with thicker ice at the grounding line, faster flow, more calving, and there's a big uptick in the pace. And this is really where we've just like eaten back into that really, really deep incised trough. And that's where that really sudden peak in the pace of ice change or ice loss is happening. And it's happening within a few centuries in this simulation. And to note, this is a simulation. This is an RCP 8.5, super high emissions. This is a scenario that's actually closer to current policies. So nationally, determined contributions sort of policies that get us to about +3 degrees warming by the year 2100. And we're still seeing something like this in West Antarctica when we include these brittle processes. And it's that deep bedrock that causes that uptick in the pace of the ice loss.
Thanks a lot. No, I worked on Gondwana sea ice incised valleys, and they tend to be much higher in energy than land ice from the Pleistocene glaciation. The incised valleys, they are much lower in velocity and all that. So I can see what you mean. Yeah.
Question. Thank you. Question at the back.
Hey, Rob, Alessio Rovere here. Hi.
Hey, Alessio.
I wanted to, as there are quite a few field people in the room, I wanted to ask you one tricky question. If you had 1 million euros to give some of us, would you ask us to refine what we know from, say, the Pliocene and the last interglacial, or would you ask us to go out and, find more benchmarks like MIS 11, MIS 9, or something like that? What would you be? I mean, what would be your priority in terms of more field data?
Oh boy, ultimately, I'm really interested and fascinated by the last interglacial. And Alessio, you've opened up the door to me. I've been thinking a lot about the last interglacial because, we have some constraints on the amount of both ocean warming and in atmospheric conditions. I think, until we get maybe longer ice cores that extend potentially even like to marine isotope stage 31, if we get more than million-year-old ice. Right now, I think all eyes are on the last interglacial, and there's still, I've been really intrigued by the work of people like Perry Spector and John Stone and others who are trying to gain an exposure age perspective on what West Antarctica has done. And, they've been looking at data, for example, from the Parrot Hills, which is here in the modern West Antarctic ice sheet. And some of those data are implying that at that location in West Antarctica, they see no more than 150 meters of lowering during the Pleistocene. And in every one of the ensembles, 200 ensembles that I showed previously that are able to match the last interglacial sea levels, there's way more thinning at those locations than the exposure age data would imply, because you're so close to the grounding line. There's the location of those Parrot Hills data. Every single one of my simulations violates the exposure age data if either they're interpreting the data correctly, maybe that there are multiple ways that we could interpret the data. Maybe we're under resolving the Nunatak region where those data come from. But, that's a fundamental problem. So like, I've been playing around with like, well, where is it possible that West Antarctica did contribute the sea level that we're seeing during the last interglacial? What would it take? And so I've been doing things like thinking about, well, what if you just had warming that, there was a lot of heterogeneity of the warming during the last interglacial. Maybe it was either concentrated in the Weddell Sea or the Ross Sea, the Wilkes Basin, the Aurora Basin, and other folks have looked at things like this too. I know Nick Gollage has done work like this. And we can look to see like, well, maybe maybe it wasn't the West Antarctic ice sheet, and maybe that's not the most sensitive because, like I was saying, the low viscosity mantle could slow retreat of West Antarctica, and maybe it slowed retreat during the last interglacial, making these other regions actually the main contributor to past sea level change. And so I took 5 degrees of warming and just targeted the Aurora Basin or the Ross Ice Shelf or the Wilkes or the Weddell to see what would happen, or the full last interglacial forcing that we think best represents Antarctica. And in every case, the Amundsen Sea embayment is the easiest to get retreat to happen. But, you can get, essentially the same amount of retreat out of, let's see, in this plot, here's 5 degrees of warming in the Amundsen Sea, but here's 5 degrees of warming if it was targeted over the Wilkes Basin, and you end up with the same equivalent sea level change, but coming from a really different part of the ice sheet. So, I think for me right now, Alessio, is, where we have reasonable climate information at the same time as sea level records, like the last interglacial, I see it as maybe being right now a really important target, and the one that I'm hopeful that we can get some better constraints on soon.
Okay, thanks. We're working on it.
Thank you all. All right, unless there's any more questions, it's time to go to the final part of our conference, a discussion, which is led by my conveners, co-conveners, Ed Gasson and Natasha Barlow. So if you two would like to come forward, please.
So we'd just like to then move to our panel session. So Flo, who's up there, can you come and join us at the front? Sarah and Rob are joining us virtually. Alessio has to navigate the joys of rush hour in London, so he unfortunately is going to have to leave. But he's already raised some, some good and interesting points. So thank you very much, Flo. Sorry, you're now on. You're with us, so you're not entirely here. So we've got up on the screen here, and Derek, bless him, up in the gallery is currently doing some amazing multitasking that I'm watching. Sort of 4 key questions that we think are the sorts of things we'd like to try and, focus on this discussion. We've got about 30 minutes or so, picking up on some of the points that have been raised through the course of the last 2 days. Rob, as ever, raises some really interesting observations that are good things for us to consider. So in particular, given the limitations of paleo sea level data, and I think all of us who are data scientists, such as myself, are realistic about this, how can paleo be used to better understand the future? What can be done to better and improve both data sets and models? It's a little bit like the question Alessio just asked, Rob, though I like the fact Alessio is lining up his next grant application. Or should we also just be realistic as to the limitations of paleo? Obviously, this is largely a paleo audience, so maybe this is a biased question. And how do we also encourage policymakers to look beyond 2100? As I said before, Alessio and myself, along with our colleagues Jackie Alsterman and Jeremy Shakan, have for the last 5 years led the PALSI working group. And at PALSI last year in Singapore, some of these questions were raised. But this is a slightly different audience, so we thought we'd re-raise them. And one of the reasons for that is that within the IPCC AR6 report, and this is in no way at all a complaint at colleagues who were involved in that, and many of us were involved in the peer review process, there is also a statement that slightly challenges the usefulness of paleo sea level data and how useful it is. And I think some of that's entirely valid, to be honest with you, though there is you know, maybe the wording in that exact sentence is occasionally being taken out of context since. So some of this discussion builds on the conversations we had in Singapore last summer, both at PALSI and at the World Climate Research Programme meeting, and also, you know, sorts of things as conveners we've been considering. Ed's obviously on the stage as a convener himself, but from a modelling perspective, and I know certainly has worked in this space. And, you know, likewise from my own view, trying to, you know, work with policymakers, practitioners to see how we can make use of some of this information. So that's a very long preamble, Tasha, and my voice is entirely going. I think let's just get started then. I think, you know, we've just heard from Rob. So Rob, I'm just going to let Sarah and Flo just respond to the first question a little bit first, and then we will obviously open this up to the floor. Those of you online, please also, could you share the screen online?
It's okay, no, sorted.
Is that sorted? Right, sorry, we're trying to multitask. For those of you online, please continue to use the Q&A. Those of you online who are logged in as panelists, you can't use the Q&A, so please use the chat, and Ed and I will try and watch 13 things at once. And also we've got some other things about sort of science communication and data representation as well, that a couple of people online, particularly Jim and Mike, have given us some links to have a look at. So if you've got time, we're going to also have a look at those links. So Sarah, as you are online, given the limitations of paleo sea level data, how can they be better used to understand the future? And I know you picked up on some of these things in your talk as well earlier today. So I'll let you respond to this first.
Sorry that my kittens are sitting on us. They've just woken up and they won't leave the room. So I think that, well, I still stand by this concept of we can't see what's going to happen in the future, but we have this wealth of information about what's happened in the past. And today we've talked about the last interglacial, deep time, LGM, and they all tell you how ice sheets and sea levels interact and the rates. And I don't understand why that's even a question of argument. Perhaps I don't know what the concept of how paleo data was used in AR6 was ever a problem, but if we don't understand or we can't accurately predict things in the past to some level of degree, how do we know that anything we're doing to 2100 or 2300 isn't just garbage? I suppose there's a long-winded way of saying it. If we can't reproduce the last interglacial or MIP, any old plyo MIP or the LGM with these models, sea level models, climate models, ice sheet models, and then we're using them to make suggestions of what's happening by 2100 and 2300, how do you know they're correct or doing what they should do if you haven't tested them? I suppose that's my first thought of it. And that limitations aren't a problem. It's just being aware of them and using them correctly. That's my way of thinking about it.
Yeah, I think that's very valid. Thank you. Flo, do you want to add anything? Obviously, you know, presented some great stuff in your talk. Is there anything you want to add in this space?
Probably there are two aspects that could be very important to convince people about the usefulness of paleoclimate in general. I mean, the first thing is paleoclimate data and also paleoclimate in general help us to understand the sensitivity of each component of the climate system. And I think this is still something, as I said, that we are struggling with both climate and ice sheet models. So I think the importance of paleo data in this is very critical because they provide different climatic context. So it's a playground for understanding a bit better the physics that we have in our own models and the gaps. And the other aspect is probably that we are lacking some physical process. As Rob said, for example, there are a huge range of brittle processes. We ignore everything about it. So we are only trying different parameterization, different physics. But paleo data are the only ones telling us that this happened or this could happen and in how much time. So it's both a collective effort in this case for the observation community to better interpret and understand the proxies also, because I mean we are far from, I think, understanding the extent of all the proxies that we have. So yeah, paleo data is now, I would say, everything that we have to improve the models that we have right now. I mean, perhaps a bit exaggerated as statement, but I think it's better than having nothing at all, I think.
Rob, obviously you've just spoken about this a bit. Is there anything else you want to add at all?
No, I think it's a great discussion. I mean, maybe this point wasn't made clearly enough, but showing like 200 different versions of an ice sheet model, basically being able to all match the satellite era of ice sheet change, makes you realize that we really do, as Sue is just saying, need paleo constraints, because when we took those 200 different versions of the ice sheet model, roughly, well, less than half of them were able to come close to matching either the Pliocene or the last interglacial. And in fact, almost none of them were able to match the pace of ice loss implied by some records of early last interglacial sea level rise, like Andrea's Seychelles record, for example.
Mm-hmm. Can I just follow up and I say, I don't think data should be used in isolation. So from my own work, if I'd only ever used sea level data to constrain my model or GPS data to constrain my model, I would miss so many other processes and information about the ice sheet. And what I think has been nice about this section is everyone's talked about slightly different data. I mean, Alessio talked about shorelines. And I think rather than saying what's wrong with paleo sea level data, it should be, okay, well, paleo sea level can tell us this. What other information can we combine from, I don't know, shorelines, cores in the ocean to fill in the gaps to make a more complete data set? So maybe that's the better thing, combine things. Like we combine models, you combine ice sheet models and climate models, I don't know, combine sedimentology with sea level data, I don't know. I've lost another example of a data set.
Yeah, no, Sarah, you're right. And I'm aware currently that we've got 3 people modelers on the panel, and the data scientist has left. And at the risk of everybody listening to me again as the data scientist, is there any data scientists in the audience who would like to comment on this particular point? Otherwise, you end up hearing from me repeatedly. No silence.
I've got something to say about the, sorry, I sort of threw that hand up. Well, I was going to talk about the data, and it's I guess it's answer Alessio's question about which time interval is most useful from a modeling perspective. And I think actually like diverse time periods are useful because we can't capture everything in like the ice sheet model response from one time period. So we do need all these different time periods. So for example, like the transition where we get lots of surface melting over Antarctica is a very warm climate, whereas what happens to the marine ice sheet happens, for example, during the last interglacial, but we can't capture all of those different states and responses just by looking at one time interval. So I think it's really nice for this meeting, we've got people looking at different time periods. So I think they are all useful to us as models.
Yeah, and you just need to press the button on your mic when you speak because they can't necessarily hear you. Okay, Tina, do you want to speak? And then I'll read out what Ken's got to say.
Sure. I think from a data perspective, I just want to say that I don't think I find anything more enjoyable in science than what I've seen over the last 10 years, which is the interaction of the ice sheet modelers with the data community. And that is probably biased because I'm working a lot with Ed and I listened a lot to Rob, and it's, both of them are kind of on stage here right now. But I think this kind of pinging back and forth of getting new constraints and then kind of seeing what the, models need to do to meet these constraints are really amazing. And just kind of listening to Rob's talk as well, right? It's coming from an Eastern Arctic perspective, like even being at a stage now where we can all say, well, we probably always all thought Western Arctica goes first. Maybe Eastern Arctica, parts of it do go first, and be open for that, and engage in that dialogue and do that together, I think is super valuable. So I think we're doing something which is incredibly useful for the future. And if we keep talking, we'll get there.
Yeah, absolutely. I couldn't agree more. And it's been really noticeable, that shift in the last 10 years. I think that's very valid. So Ken Miller has said in the online chat, the past tells us about different planets. They may be all Earth, but they are Earths with different CO2, ice volumes, temperature, biota, and further back different geographies and polar input. Each provides a different experiment on how the Earth black box works. The most useful for projecting the future are those that at the peak warm intervals, such as 5E, 11, Pliocene, Miocene climate optimum, but all contribute to our understanding of how the ocean climate system works. Crikey, there's no pressure reading out a message from Ken Miller. My God, I feel stressed. And then Jim Gelder has also posted and said, I'm just an engineer, but we use the concept of the geotechnical triangle to talk about the relationships and tensions between conceptualizing a problem, getting data, modeling the data, and tempering the experience and empiricalism. Oof, I'm dyslexic, so reading on the fly is really hard. And testing it with feedback. In this context, paleo has a key role in the context, experience, and feedback as it controls the understanding of the data and also its limitations and how it influences the model. I often find that as geologists' input to conceptualizing the problem, it is key to unifying the different disciplines in engineering design, and I see a really strong analog here with paleo providing the context. And that's actually really interesting because the GeolSoc ran a meeting joint with the Quaternary Research Association at the beginning of this year, which is the national body, jointly trying to bring together academia and industry. I was attending that meeting with my offshore wind hat on, but it was another illustration, in fact, where we're using similar data sets to try and bridge that gap. So thanks, Jem. I think that's a really valuable point. Anything else from the floor in regards to that particular question? No. Yes, Fred.
So I'm not sure whether I'm actually skipping ahead a few questions, but I guess from a sort of more modeling perspective, one thing I think we can potentially do a bit better to kind of collaborate better with data collection people is that actually there's some increasingly you can use statistical approaches to work out if you had a data point in this location, how much extra information would that add to your model? And I think definitely as modelers, there's also the chance to essentially help kind of guide where field sampling should be concentrated based on where you're going to get the most information in terms of constraining certain ice sheet extents through the time or, you know, global sea level changes.
Somewhere some things are moving. Oh my God, too many things at once. Oh, my watch has told me I have an abnormally high heart rate. That's probably valid. Okay, thanks, Fred. That's really useful. I'm sorry, I'm confused because I saw a message and it's disappeared. Let's move on because I'm just mindful of discussions and at risk of talking about paleo all the time. And maybe this is something to consider in regards to the other questions, is what can we do to improve paleo data sets and how therefore can they be more useful? Flo, do you want to, or not necessarily just data sets, but models, how do we try and improve them to make them more useful for the future? Is there goals we should have as a community? No pressure.
Well, I think what we are really interested in to implement adaptation actions is the rates of sea level rise. And I think it has been decades that we are trying to focus on these metrics. Well, getting the right rates of sea level change, for example, both in the past and in the future is something complicated, both in the model and data. From data perspective, it requires that we collect expanded sedimentary sections, so to be able to make high resolution sampling and catch the right variability. So it means that it's very tricky to find, especially in polar areas, because we need to find sediment traps somehow, so it's very localized. On another hand, from modeling perspectives, well, I mean, it's not because we catch up with, for example, high spatial resolution that we catch up with high, let's say, climate or ice sheet dynamic variability. So I would say it's to me, catching up the right rates of sea level rise, it's a system problem because we need to catch the ocean variability and atmospheric variability right. So to provide the right input to ice sheet models. So yeah, I guess we need to make some step in with toward the direction of Earth system modeling, I would say. So high resolution data, I mean, paleoproxies, and I would say a better coupling between the different components of the climate system.
Great, thanks, Flo. And in fact, the missing message has just come back. I'm having to watch 2 accounts at once. And in fact, it's from Malcolm, and it sort of builds on this himself in saying it's about also engaging with different disciplines. And that sort of is relating to what you're talking about. And particularly, he highlights paleontology, which might allow us to assess biota as an assessment of rates. And that's sort of an illustration of the octopus paper that Tina and I both love, the octopus paper, as a good, really good illustration of how those different disciplines can come into play to tackle some of these Earth system questions. Sarah, anything you'd like to add in this space?
So this is maybe controversial. I want to make the point that more data and more models is not always better. On the proviso that, because I work in the UK, there's an absolutely shed load of sea level data, but that doesn't always, there's a shed load of sea level data in a really small area. So it doesn't necessarily mean that the ultimate aim should be get more sea level data from the UK. And I think that there was the paper by Nicole Kahn about the PALC database of making better databases of sea level data. And it was from that you kind of were like, okay, then this area's got loads of data. We don't need any more data here. So by kind of combining them all into databases, it made more of the point of where do we need more data and why do we need it? So you can run hundreds of GIA models for hundreds of simulations of different ice sheet reconstruction, but sometimes I think it's useful to step back and say, why? Because then, Mel, maybe it's because I think this all costs money to run them and it costs money to, I don't know, store the stuff. So yeah, be careful about checking everything we have already and where we need information, kind of thing. That was a bit
totally. Yeah, and I had some context there is we had a meeting in 2014, I realise now, where we tried to come up with these standardised approaches for the Holocene databasing, which then Alessio's picked up and run with for the last interglacial, and those are trying to be applied more broadly so that if we standardize things, do exactly what Sarah says. The reality is more sea level data points from the UK is probably not the answer, but there are certainly data gaps that could be key. Rob, anything you'd like to add?
No, I appreciate Sarah's perspective on that. Great comments.
Anything from the audience at all?
Hiya, Georgia speaking. So yeah, just in terms of how we interpret paleo, and as kind of Ken said, you know, having that the different Earths, in some sense, the concept of, you know, particularly for the mid-Pliocene sea level above present, doesn't really capture ice sheet sensitivity or climate sensitivity or the rate of processes, because that's from modern. What we need is Pliocene glacials to be that starting point. What's the change from that glacial to interglacial? Kind of increasing sea level from present isn't, but with, you know, that starting point may be warmer or cooler than present, and I think that's something that we're missing, and we need to make sure that we're considering the context of those changes in the Earth system at that time. That's all.
Couple of comments down the front here.
Thank you. I suppose looking back at the question, what needs to be done to improve paleo data sets and models so they can be more useful? Useful to who? And I think that's, I might be diverting the conversation slightly. I think we as a community have done a fantastic job at understanding, quantifying, and reconstructing, predicting sea level change. But what about communicating sea level change? For me, in terms of useful, and it goes on to the last question about policies beyond 2100. Tasha and I briefly had a conversation last night about how, you know, we use our friends and family as a gauge to what do people understand about sea level change. And is, you know, if for me, it feels like we're going down the Leonardo DiCaprio film route, whatever it's called. The Only Way Is Up was, I can't remember what the film's called now, but we know something's happening. We know sea level's rising, but everyone's somewhat not. It's not the necessary right term, but people are relatively ignorant of that understanding. And we have all this data. We need to communicate this data, and I think we need to. I don't think we need to improve our data sets. I think we've got fantastic data sets. Yes, we'll continue to refine them, and we'll continue investing in them. But I think we need to there needs to be a bit of a sea change in communication to the wider public to actually help a global audience, not just a British audience, but a global audience, to understand the implications of what we are predicting to happen in the long term.
For me, the holy grail still to include is the ocean currents, the seaways, and their influence on the weather patterns and on global meteorological things, because that's important not only to understand the past. We had that yesterday, that discussion with Ray, where he showed the example from Malta, where it's very important, but it's also in the future forward looking, like, for example, the simulation of AMOC. Is it shutting down? Is it advancing? Will it continue? Has enormous impact on the near future.
Yeah, absolutely. And I think, you know, work that you've been involved in and others have been involved in is trying to integrate that climate aspect. Do you want to add anything to that? Press the button on your mic.
Sorry, mine doesn't work. Yeah, I guess it goes into what we need in the models in particular, and I think there's a big push at the moment for ice ocean coupling. That's a big area, and there was a question earlier about how sea ice is coupled to the system. That's a massive area, and we're only just starting to do that. So I think that's, from a modeling point of view, is really exciting.
Yeah. So I think, thanks, Tom, for a very nice segue, most appreciated. I think we'll just move on to that kind of, how do we look beyond 2100, or bigger question, how do we communicate our science? And you're very right, to whom, because the communication approach will vary from audience to audience. We're going to bring up online a couple of, yeah, thanks very much, Derek. A couple of websites that have been highlighted to us by Jim Gelder and Mike Bigwood through the virtual online meeting. Just as kind of, I'll be honest, these are websites I wasn't aware of. I think a lot of us are used to kind of the climate central flooding scenarios that I'm sure those of you who teach use regularly in lectures. But there's just some nice illustrations here. This is one as to kind of what different sea level rises look like in regards to different cities. I think that was a nice. I can't remember, Jim and Mike, which one sent whom. I'm very sorry. So apologies, because it's somewhere a mile up the chat. And then Derek, can we switch to the other one as well? That was a second. Yeah. So here's another one. Like the premise here was kind of, you know, illustrating sort of gigatons of carbon dioxide, but there were all sorts of things on this website of like things you might understand, whether it be CO2, whether it be population densities, poverty, for example. And I think that off the back of AR6 and the SOROC report, there were some beautiful visuals done by sort of third-party groups in particular. And these kind of infographic things are very powerful and can be used with a range of different people. And I'm sure there's people in this room have a lot more experience on this than I do, but just wanted to highlight these couple of examples that were brought up just in the online chat to make sure that we fully integrated everybody as part of it, because I think they're really nice illustrations. So thank you very much for that. Oh, here's another one. Derek looked at these more than I have, so I might end up having to get Derek to tell us what's in each one of these. But you can see there's all these different categories here, for example. So yeah, we're trying to share those for people in the room to who are not online to be able to have a look at as well. They certainly were websites that I was not aware of. Okay, so if we can go back to the questions then online. So how do we encourage people to look beyond 2100? You know, Rob, you've been working in this area. I know this is something that you communicate with people quite regularly. Do you want to provide some perspective here from your own experience?
You know, the year 2100 is getting closer and closer. It seemed, you know, when it was a century away, it seemed like a long time. And now, you know, it's 3/4 of a century away. And a lot of our coastal infrastructure, things that we're designing and building today, are going to long outlive the year 2100. I've been working with some different indigenous groups, mostly in North America. And some North American indigenous cultures have a 7-generation perspective. That's their target. So more than 200 years. And it's, you know, that's, to me, is a, I really just love the spirit of that. You know, I think getting beyond the 30-year sort of mortgage cycle continues to be a challenge. But, you know, even American cities now looking at aging infrastructure and seeing buildings and iconic places that are either approaching or more than 100 years old, to me is one way to sort of drive it home that we need to have a longer term perspective. A lot of the changes too that, I mean, wasn't able to get into this here, but like once the retreat begins, like in Antarctica into these deep basins from a modeling perspective, a lot of the change is irreversible, even if you return to like have carbon dioxide reduction and return to basically pre-industrial CO2, you know, because once we've put enough heat into the ocean, because Antarctica and the ice sheet is interacting with the ocean waters, it's going to be a really long time before things reverse, even slow down. So the issue of irreversibility is another, I think, really important data point. You know, if we can say more to, again, to both the pace of sea level rise and then, you know, details maybe about the rate of recovery and how they are linked to certain processes might be important and impactful. So I don't know if you talked much about irreversibility yesterday or.
No, we didn't, Rob.
So I think again, this community has a lot to bear on that issue. You know, people think, well, I think that a lot of the lay public just assume that if we start to get our act together and start reducing emissions, that from a sea level perspective, that everything's going to be okay, and it's not. So thresholds, reducing uncertainty in thresholds. The modeling work that we've been doing suggests that once you start to approach and maybe just exceed about 2 degrees Celsius for a global mean, then stuff starts to get scary for Antarctica and Greenland. You know, roughly, it's interestingly roughly about the same temperature threshold for a big kick up in the pace of change. And again, once things start, we get those grounding lines to start retreating into that really, really deep bedrock. It's not going to slow down.
Okay, great. Thanks very much, Rob. Flo, is there anything you want to add in regards to kind of this looking beyond and communicating our science?
Actually, I think the concept that Rob's just explained is powerful. I think the question of cultural heritage is something that we sometimes approach, but so far we tend to avoid to really approach because it seems not something very concrete, let's say, or very practical. However, it's really important because it's about cultural heritage, it's about geographical heritage. So it's about the evolution of our, let's say, civilization and also planet. Another aspect is if policymakers are really concerned about the policy that they are trying to implement, there is very few difference among the different scenarios by the end of 21st hundred. So the difference really rise up when we look beyond this threshold. So a multi-centennial perspective is important also to understand the efficiency of the implemented policies. So that's a bit more practical aspect. So, and I think also talked recently to different practitioners and policymakers, and they are more and more concerned about the efficiency of their policy because anyway, it will be costly. So if we really want to transfer something so on more heritage level, then we need to care about the efficiency of the policies. So it's all linked together.
Great, thank you. Jim's also added here that actually sort of things where we can see stuff and it's therefore easy for people to visualize, such as, you know, this raised shoreline here, or we've got these illustrations I shared on Twitter this afternoon, a picture that Chris Stringer had shared about Trafalgar with hippos in it, or Italian caves with beaches in it that humans were once occupying. Those are often things that are easier for people to kind of, you know, get their head around than necessarily lines on graphs are lovely to us, but often hard for people to be able to communicate around. And this idea of storylines is something that in particular was picked up by the IPCC. And I know Matt Palmer at the Met Office is very keen on that as an idea as well. Sarah, anything you'd like to add? You're on mute.
Garbage. That was just because the cats were poking me in the head. If I ever talk about sea level rise to non-academics or my non-friends that haven't heard about my PhD, they just think it's really simple and we just all move up a hill. That's all they ever tell me. We're just going to move up a hill. And I think maybe you have to think about, okay, sea level rises will all live on a hill, but where will we get our water? Where will we get our food? Where will we get our energy? And maybe if you were trying to make it more of a public knowledge, the sort of sea level rise concept seems to miss people. But if you said, well, we wouldn't have any fresh water, you wouldn't be able to make any food, you'd all starve to death. Sort of like more things that people could, maybe it's a bit drastic, maybe things that people could think of as an impact on their day-to-day life, rather than we'll just all go live in Scotland, which is kind of the reaction I generally get from people. And I don't know why 2100 is a number, because if I have nephews or small children, that's their lifespan. And you should be thinking about your grandchildren's lifespan, so to speak. And my last sort of strange way I think about this is, whenever you watch a weather forecast and the weather forecast is wrong, you're kind of fine with that. And you kind of go, well, it was roughly right, because they didn't say there was going to be a hurricane and there wasn't a hurricane. But whenever we make projections or AR5 and we say, well, these are the limitations and these are the ranges, it seems to be thrown back that, well, why aren't they 100% correct? And it's like, we're not allowed to have the weather analogy sort of accepted in the predictions and the models. They have to be a value and that's it. Now, if we took that approach with the Met Office or whatever, every time they made a weather forecast, we'd be up in arms, because every day it says it's dry in Sheffield and it rains, sort of thing. So maybe there's a different, maybe it has to be saying it's okay for them to be a little bit wrong, or they have limitations, because that's just human life. Anyhow, they were my ranty points.
Thanks. We've got Jim Gelder on the screen now, because Jim, hi Jim. Jim's been part of our virtual audience for the last 2 days and has been adding some really interesting stuff in the chat. And instead of me just keep relaying it, I'd just like to give Jim a minute or so to speak. Jim, do you want to add anything? You're on mute. We've done quite well until the end of the meeting for the on mute bit. So.
I managed to take gold right at the end of the meeting. Fantastic. Continuing what Sarah's just said, really, I was at a Floods and Coast conference a couple of years ago now. And I've worked on flood defences and that sort of thing around the coast for a few years. But there was one talk, and it was about abandoning a village on the North Wales coast because it was no longer economically viable to protect it. And to be honest, it made me quite emotional, because it was all stories of people's livelihoods and sort of three generational stories of people in this village, and how the council were having to find land to build new homes for them, and then all the business of decommissioning the infrastructure and the gas pipelines and things like that. And it was such a human story about a process that's going to be happening more and more and more over the next few decades. And I just see, as geologists and things like the raised beach and that ability to give people a perspective that just isn't there in the public narrative at all. You know, the fact that sea level has changed by meters or tens of meters or hundreds of meters in relative short periods of time. It's not a thing that's out there. It's not a thing that's understood. So I think taking two dimensions, really, one, our sort of four-dimensional worldview as geologists, and then the very human impacts of what a small amount of sea level rise will mean to communities. And you'd have to do it for different communities in different countries relative to the policymakers that are there. But I do think we've got a really strong role there to fill a gap of sort of conceptualization and scale that just isn't out there in the public. I was talking to my wife about it last night and thinking, you know, we need the David Attenborough of geology and climate science, and somehow make the rocks as cute and cuddly as seal pups. I don't know.
Yeah, that's hilarious because actually I literally sent an email last week to Chris Jackson, who some of you will know leads up some of the TV programs in the UK on geology, and said we need the geology David Attenborough. So I literally used the same phrase. Okay, I'm just mindful of time. We've got a few comments come through, which is also going to be joy because my laptop's about to die because I don't own a Mac and PCs are rubbish. Yeah, they're also on the big screen, but they're going through so fast I can't always see them. So Ken Miller has said we need to address skeptics. We need to address the skepticism that we know sea level will continue to accelerate. A meter by 2100 was double our estimate in 2007 and is now where we're tracking. Rob made some good points about city planning and infrastructure, and we will reach a meter sometime in the 21st century. And then Anne, I'm really sorry, Halibustart, I'm really sorry, I pronounced that really badly. I just want to comment regarding the general response that we'll move up the hill. That's definitely something I've heard before. We really need to also build public understanding of the global picture. For what about Lagos, as was shown today, or Singapore, India, coastal countries? And I know we have many Pacific Island nation as representatives at the WCRP meeting last summer. That's really important. I totally agree. So Anne's then added that, meaning that folks don't understand the huge global implications of coastline change for low-lying communities with less resources to adapt. And that piece, that the location that Jim refers to is Fairborn, and I've been asked to comment on various media pieces about Fairborn over the last few years. And in fact, a paper came out from Social Sciences in regards to Fairborn and what it means in regards to that community response in the last couple of weeks as well, really highlighting, Jim, some of the points that you're making about those very human stories. That's for those of you interested in a UK context, it's really important. Ken's also raised a book called The Drowning of Money Island, A Forgotten Community's Fight Against the Rising Seas for Ever-Changing Coastal America, which was published in 2019, which tells stories of sites in New Jersey, which are similar to those in Wales. And then I think Sarah's now gone, but Sarah and I will remember for many years visiting some sites in New Jersey about 15 years ago, where again, very similar things, where these coastal communities were a significant threat, and the human stories associated with those. Okay, I'm going to close the online chat because I can't keep up any faster. Is there anything final additions from the room at all? Deirdre.
Hi, is the microphone on? I can't tell. I know that policymakers are having a hard time responding to their constituents, and that is something that we need to address. But the business world is very aware because this is going to cost a lot of money. There's something called the Task Force on Climate-Related Financial Disclosures that has been created. You've got big consulting companies like Deloitte now that everybody's probably aware of, hiring climate advisors to help them sort of help the people that they're consulting for develop these climate adaptation plans, sustainability plans. So policymakers might not end up being the ones that kind of drive these changes. It's going to be the business and financial community. We need Rob Barnett here because now he's doing all that stuff.
Yeah,
but,
we do.
So that's the comment I wanted to make.
Great, thanks. And then we'll give Georgia the last word.
Yeah, two things quickly is aren't we the people that kind of make that 2100 mark?
Valid.
We should just be adding 100 years to every year, and that's what we report. I know that 2300 further isn't that easy for every model to do, and therefore the comparisons become weaker. But yeah, I mean, I think that's on us. And then with the communication thing, I kind of just say, go home or go to your nearest beach, your nearest community. I think it has to be all of our responsibilities. There's no real way to make this global kind of problem accessible for everybody. I've kind of recently just gone home and done that and spoken with the community, and from the 2 kilometers kind of difference, what the sea level rise that they're experiencing is vastly different, and the geological types, one's a sandy beach or one's a rocky beach. Neither of them are really going to get inundated. They are going to get salinity intrusions, and they're going to get flooding. there's just no way to have a single conversation with a nation, and certainly not with a globe. It needs to be individual, and if it needs to be personal.
Great, thank you. I think that's a really great thing to be able to end on. Really some valid points. And I know sometimes we sit in these discussions and think, well, what's it added? But in some respects, the project that Tina presented is a perfect illustration that these things can then snowball, and we can end up going and collecting the new data points that are the right ones that we want. These come out of these conversations. So thank you ever so much for everybody's contribution. Ed, anything you want to add at all? No, we're happy. Okay, well, in which case, given Dan's absence, it falls on to me, I think, probably as I'm stood here, to just close the meeting. Firstly, we'd really like to thank Derek up in the projection room. His ability to multitask is next level, because I have about 14 different things on my screen at the moment, and think he's about to put up the links for the yes, here we go. He's been writing this as I've been watching, the links that Jim and Mike showed. So for those of you who have not been on the online chat, you can have a look at that. We'd also like to thank the GeolSoc, in particular Amelia. Amelia's now had to leave, but Natasha's here as her representative. So thank you very much to the GeolSoc for their support as well. If we can give them a round of applause too. Dan emailed Ed, Dow and I about 8 months ago and said, would you like to be involved in this meeting? And I initially said no, I had too many other things on, but here we are. It's been a pleasure. And thank you everybody for your contributions. It's been fascinating to be able to explore sea level on such a range of timescales. I often find myself stuck in the last interglacial and the Holocene. So it's been lovely to be able to consider these on such a wide range of timescales. Thank you to our invited speakers and to all of our panelists, and we wish you a safe journey home. Thank you very much.